lambda function directly. Notice that we are passing in our arguments as double literals. Okay, this is how you can set up a lambda function that takes parameters and call it directly. Another thing we can do is make our lambda function return something. And that's really simple. We're going to set up the lambda function like this. So it's going to take two parameters, a and b. And here you see that we are returning a plus b. And we can do that. The lambda function is now going to return something. And this entire thing we have here is going to be a lambda expression. The lambda function is going to be called, it is going to return something. And what the lambda function returns is going to be assigned to this result variable here. And if we print it, we're going to get the sum of whatever we pass in here printed out on the console, and we're going to see it printed out on the terminal. It is also possible to put your lambda function directly in an output statement. I realize this can be really confusing, but please look at this entire lambda function thing here as a single value. Because this is a lambda function that is going to return something, and what is returned by this lambda function is going to be printed as our result here. Again, I realize this may be confusing to many of you guys. We are going to head over to Visual Studio Code in a minute, and we're going to see this, and you're going to really understand. Okay, the last thing we're going to look at is that we can specify a return type to our lambda function. And the syntax to do this is to do a dash, a greater than symbol, and put your type after that. And when you do that, now this lambda function is going to be forced to return double type. Even if you pass it to parameters that are not of double type, we are going to add them up, and the return type is going to be implicitly converted to double, and that's what we're going to return. And we can print it out on the console, and we're going to see an example of this in a minute when we hit Visual Studio Code. In fact, this is really all I had to share with you in the slides. I realize many of these things may be confusing. We are going to head over to Visual Studio Code and play with these things step by step, and I am sure you're going to understand. Here we are in our working directory. The current project is declaring and using lambda functions. We're going to grab our template files and put them in place. Let's do that. And we're going to grab our folder here and drag and drop it in Visual Studio Code, and this is going to open it. It is opened here. We have our main CPP file opened. We can close the left pane here because we don't want it anymore, and we can clean up our function here. And the first thing we're going to do is to put in the syntax for a lambda function here and use it as a reference as we learn about this. I think this is going to make things a little easier. So the first thing we want to do is to declare a lambda function. And the first thing we need to put in is a capture list. A capture list is going to be englobed in these angle brackets. So this is our empty capture list. And after this, we're going to put in a parameter list, which is going to live inside these parentheses here. After that, we're going to put in an optional return type. For now, we're going to ignore this. And after that, we're going to put in our pair of curly braces. And inside this pair of curly braces is where the body of our lambda function is going to live. So inside here, we can do whatever we want in the body of this lambda function. For example, we can say hello world, which is the logical thing to do at this point. So we're going to say hello world here, and we're going to put in our new line character with ENDL. Okay, now we have a lambda function declared, but we have to put in a closing semicolon because this is a C++ statement. Okay, now we have our lambda function declared, and this is valid C++ code. If we try to compile this program, you're going to see that it is going to compile fine. Okay, build finished successfully. And if we try to run it, it is not going to do a thing because we are declaring the lambda function here, but we're not calling it to get it to do things. So let's bring up a terminal and show you that if we run this program, it is not going to do anything. So let's do clear and run Rooster. You're going to see that it's not going to print anything. And we can even go down here and put in a closing stdc out statement saying done to mean that we are hitting the end of the function here without doing anything. So if we build again, the build is going to be good. We can clear and we're going to run Rooster. You see, we are printing done. We are hitting the end of the function here, and we're not seeing hello world. So this function here or this lambda function here, to be exact, is not being called. One way we have to call it is to give it a name. And we have seen that to give it a name, we have to assign the entire lambda function thing we have here to a variable. And we're going to use autotype deduction here. So we're going to say autofunc, and we're going to assign our lambda function here to this variable. And this is going to be basically a handle we have in our program here to the lambda function. And we can use this handle to do things with the lambda function. But by now, I want you to see that even if we run the program now, it is not going to do anything because we're still not calling the lambda function here. Let's show you that. We're going to build again, and the build is going to be good, no problem. We can clear and run Rooster. Still not hello world because we're not calling our lambda function. To call our lambda function, we have to use our handle here, which is this variable, and use regular function called syntax. So we can go down here and say func, and we can put in our parentheses. We're not putting in any parameter because this lambda here doesn't take any parameters. And now, if we run this program, it is going to say hello world because this line here is going to call this lambda function. Let's build and see that. We're going to use GCC to build. So now, if we clear and run Rooster, we're going to see hello world. We can call this function multiple times because we have a handle to it. The handle is going to be valid throughout the scope of the main function here. So we're going to go down and call it again. And if we build, we're going to build with GCC. The build is good. We can clear and run Rooster. We're going to say hello world twice because we are calling our lambda function twice. This is one way we have to call our lambda function here. So we're going to comment this out because we're going to see a few other things. And on top here, what we were doing is declaring a lambda function and call it through a name. Now we're going to go down, set up a lambda function and call it directly without giving it a name, because that's also a possibility in C++. For that, we're going to grab our lambda function here and we're going to copy it. And we're going to say declare a lambda function and call it directly. And the syntax to do that is really simple. You set up your lambda function like we have seen before. You see, this is our lambda function statement here. But you're going to go to the closing curly brace and add a pair of parentheses. This is going to declare the lambda function and call it directly. Notice that we don't have a handle to this lambda function. So if you do things like this, you will have only one chance to call the lambda function. So we're going to say hello world once because we are declaring the lambda function and calling it directly here. And after that, we're going to say done because we're going to be hitting the end of the main function here. Let's build the program and show you that. We're going to build with GCC like we always do. We're going to clear and run Rooster. This is going to say hello world, and we're going to be done here because we are calling this lambda function once. Again, notice that now we don't have a handle to this lambda function, so we really have one chance to call this. And you will do this if you just want to set up some function that you want to call directly and you don't care about calling it ever again in your C++ application. And we're going to see that we have many kinds of problems where we want to do these kinds of things. Okay, now that you have seen this, the next thing I want to show you is how to set up a lambda function that takes parameters. And we're going to comment out what we have on top here because we don't want noise output on our terminal. And we're going to grab this lambda function and adapt it. So let's copy it. We're going to go down here and put it in. And we want to pass two parameters now. Let's pass in double parameters. We're going to pass in double A and double B. We can do that. And inside the lambda function, we can print the sum of these two variables. So we're going to say a plus b, for example, and we're going to print out whatever is the result of a plus b. Let's do that. And after we do that, you're going to see that we get a compiler error because now our lambda function is taking parameters, but we are calling that with an empty list of parameters. So we need to give it something to sum up. Let's give it 10.0, for example, and 5.0 and see what we get. And after this, we need to put in our semicolon because this is a C++ statement and any C++ statement needs to end with a semicolon. Now, try to think about what we are doing here. We are setting up a lambda function. Okay, it's going to end at this closing curly brace. And this lambda function is going to take two parameters of double type. And inside the lambda function, we are going to print out whatever is the sum of these two parameters that we are taking in here. After that, we are calling our lambda function with two variables, 10.0 and 5.0. Or I should say two double literals. That's what we are calling our lambda function with. And now, if the program runs, the lambda function is going to be called once, and we're going to print out whatever is the sum of these two numbers, and that's going to be 15. Let's build. So we're going to build with GCC. The build is good. We can clear and run Rooster. We're going to see a plus b is 15. We are calling our lambda function here. If we put in a 50 here, for example, we're going to get 60 printed out because that's going to be our sum. Okay, let's build again and see that printed out. If we run Rooster, we're going to see 60 because that's the sum of 10 and 50 here. Another thing we can do is actually not call the lambda function directly here. We can actually comment this out. I don't want to take this out because you might want to use this as a reference. So we're going to comment this out and set up another example that is going to name our lambda function, and then we will have a handle to the lambda function and we can call it multiple times. So let's take out the call we are doing here, and we're going to assign our lambda function to a variable. We're going to say auto func1. We can call this func1, no problem. And now we can call this lambda function multiple times. For example, we can say func1 and pass in 10 and 20. Okay, and we can say func1 and pass in 5 and 7. Why not? If we run this program, it is going to print the sum of 10 and 20, and it is going to print the sum of 5 and 7. And it is going to be calling this lambda function multiple times. Hopefully you can see that if you want a chance to call your lambda function multiple times, you will need to give it a handle like we are doing here. And then you can use that handle multiple times and call your lambda function however many times you want. So let's build this program and see what we get on the console. We're going to clear and run Rooster. Now we're going to see a plus b is 30 as a result of this call here, and we're going to see a plus b is 12 as a result of this call here. Notice that we are passing in integer literals. So the compiler is going to insert an implicit conversion from int to double because our lambda function here is taking double type. You really need to be aware of these implicit conversions and make sure they are working to your advantage. If they are working against you, try to find a way to make your code work exactly like you want. Because we are learning about all these cool tricks in C++, you're going to be using them at your advantage. Okay, hopefully now you know how you can set up a lambda function that takes parameters. We're going to go down and comment this out because now we want to see how we can return something from a lambda function. And we're going to be using the same lambda function here. So let's grab it. And we're going to say lambda function that returns something. And we're going to set up our lambda function here. Let's put that in place correctly. And instead of printing out the sum of a and b, we can return that. We can go in our lambda function and say return a plus b. Okay, now that we have this, we can either call it directly by saying, for example, 10 and 20. But now, if we try and run this code, it is not going to do anything. Try to guess why. This lambda function is not printing to the console directly. It is just returning whatever is the sum of 10 and 20. And if we return it, we're not doing anything with whatever is returned from this lambda function. So we're not going to print anything, and we're just going to print down here. Let's build and make you see this, because you really need to be aware of these little things. So the build is good. We can clear and run Rooster. We're going to see done. Our lambda function is returning something, but we're not doing anything with the return value. If we want to print the return value, we need to catch it somehow. And we can put that in a variable, for example. We can say auto result and assign the return value of our lambda function to this variable. Now we have a chance to print this. For for example, by doing stdc out result, and we're going to print that out and say result. Now if we build this program, it is going to print whatever is the sum of 10 and 20. Let's do that and show you that this is actually the case. So build is good, so we can clear and run rooster. Result is 30. If we pass in 10 and 50, for example, we're going to get the same thing. Let's pass in 60 here. So we're going to build with GCC. The build is good. We can clear pretty quick and run rooster. Now the sum is 70, and this is how you can return stuff from your Lambda function. And once you return stuff, you have to be sure you catch your results and print them out. Another thing you can do is print out the result directly after you call your Lambda function. So for example, we can grab this entire Lambda function thing here and put that in an stdc out statement. So we're going to put in a second one here and say result, or we can even comment this out. We don't want to be confused when we look at the terminal here. We're going to comment out the first stdc out statement here, and we're going to say stdendl here and put in a placeholder for our Lambda function, and we're going to paste it in. If we do something like this, again, this entire Lambda function thing is going to return the sum, and that's what we're going to print. I realize this syntax is really cryptic, but it is going to work. Let's try and build our program here. The build is good, so we can clear and run rooster. We're going to see that result is 70, and this is coming from our call here, which is nested inside our stdc out statement. You can do this if you want. Another thing you can do, as we have seen before, is give your Lambda function a name and call it repeatedly. So for example, we can try and comment out what we have here and set up another Lambda function because we don't want to confuse you again. So we're going to grab our Lambda function here. We're going to copy it because we don't want to type this 1,000 times. And we don't want to call this Lambda function directly. Instead, we want to give it a name, and we're going to say auto func2, and we're going to assign our Lambda function type to func1. Now that we have this, we can say auto result1, for example, and we can say func, and we can pass in whatever we want. Let's put in 23 and a 7, and this is going to add up 23 and 7. We're going to grab the result, and we're going to assign that to result1. If we go down and say auto, for example, result2, and say, for example, func1, and say 9 and 45, why not? And go down and print out these result variables, we're going to see the sums printed out. And again, the message is that we can use this handle to call our Lambda function multiple times. So let's go down and print these out. We're going to say result1, and we're going to say result1 here. We're going to go down and say result2, and we're going to print that out. And we can even call this Lambda function directly and put that in stdc out here. So let's say that we're going to say result3, for example, or direct call. I think this is descriptive enough. So we're going to say func1, the name of our Lambda function, or the handle to the Lambda function, and we can put in a 5 and a 2, for example, and we're going to see this print out the result. If we build our program, let's do that with GCC. The build is going to be good. We can clear and run rooster. We're going to have result1 is 30, which is 23 and 7, so the sum is 30. The second one should say 54 because that's the sum, and the third one should say 7 because that's the sum of 5 and 2, and it is what we have here. And after that, we're going to see that our program is done. This is how you can set up a Lambda function that returns something, and we have seen many ways we can work with this. Let's comment this out because there is one more thing I want you to see, and that's a Lambda function whose return type is specified explicitly. Okay, we are going to reuse the same Lambda function we have been using all along, and we're going to copy that. And we're going to go down and put it down here. And now we want to specify the return type as double. The way we do that, we go after our parameter list and we put in a dash symbol and we put in a greater than symbol. And then we're going to specify the return type of our Lambda function. Let's say that we want our return type to be int. This is how we say it. Now our function here is going to return int regardless of the types that we put in. So what the compiler is going to do when we call this lambda function, it is going to take the parameters, it is going to add them up. For example, now they are double. So it's going to add a and b as double. It's going to produce a double variable. Then it is going to convert that to int and return it. You notice that now we have forced our lambda function to really return a specific type here. Before, the return type was deduced from the operation that we did here. And before we were returning double because that's what the compiler was deducing for a and b here. To really drive the point home, let's assign this lambda function to func1 or func3. Let's do that. We're going to say func3. And this is a lambda function that is going to explicitly return int. And we're going to set up another one which is going to deduce the return type. We're not going to specify the return type explicitly. So we're going to take out our return type here. Let's do that. And we're going to go down and say auto result3, and we're going to say func3 and add up two double variables. Let's set up these variables explicitly so that you really see what is happening. So we're going to say int a and put in a 6.9, why not? And let's make this guy a double because that's what our function here expects. And we're going to do another one, do double b, and we're going to put in a 3.5, for example. And we are going to use these variables as arguments here. We're going to say a and b, and we're going to say auto result 4. This should be func4, sorry for this. And we're going to say result 4, and this should say result. I am making many typos. So we're going to assign our lambda function, the result of our lambda function, I should say, to result 4 here. And we're going to pass in a and b. Now, we want to see the types of result 3 and result 4 here. We're going to go down and print them out. We're going to say stdc out size of. This is one way we have to get the types of our variables. We're going to pass in result 3. We're going to say size of result 3, and we're going to go down and say size of result 4. Okay, we have our code in place, and what we want to see is the type that is deduced by the func3 lambda function here. We are explicitly turning the return type into int. The parameters we pass in are going to be double. That's what we have here. We are going to add up a and b, and the result of this is also going to be double. But the compiler is going to notice that we are returning int explicitly here, and it is going to take this double result and transform that to int. And we're going to get the result of that assigned to func3 here. For the second lambda function here, we are going to automatically deduce the return type. So what we return here is going to be a double type. And we should see a size of int for result 3 here printed out. So we should see a 4 on my system. And for the second statement here, we should see a size of double printed out. This is one way we have to try and prove this. So let's build this program and see what we get. Okay, the build is good. We can clear and run Rooster. And we're going to see that this is exactly what we expect here. If we want, we can even print result 3 and result 4 and see what we get. So let's do that. We are learning. So let's experiment with this a little bit. We're going to say result 3, and we should go back and say result 3, if I can type ENDL here. And we're going to go down and say stdc out result 4. Okay, if we build and run this, we're going to see the results printed down. The build is good. We can clear and run Rooster. Now we have result is 10 for the first thing here, for the first lambda function, and for the second one, result is 10.4. You can see that for the first one, the result was transformed from double to int, and for the second one, we deduced double, so we still have our decimal point here. Hopefully, this makes sense. And this is really all we set out to do in this lecture, showing you different ways you can set up your lambda functions. We saw the syntax of setting up a lambda function. We saw that you can declare a lambda function and call it through a name like func here. We went down and saw that you can declare a lambda function and call it directly through the syntax you see here. We saw that how we could specify parameters to our lambda function. This is the syntax. And once you do this, you have to remember to call your lambda functions with parameters like we see here. We can even use a handle given to our lambda function and call our lambda function multiple times. After that, we saw that we could return something from a lambda function, and we had many chances to play with us. And we finished by looking how we could specify the return type explicitly, and the syntax to do that is what you see here. We are going to stop here in this lecture. In the next one, we're going to see how we can use our capture lists here and make them do useful things. Go ahead and finish up here and meet me there. In this lecture, we're going to see how we can use capture lists in our lambda functions and do some useful things. We have seen that the syntax of our lambda functions includes these angle brackets here, but we haven't really used them to do anything. For what we have done in the last lecture, they were empty all the time. In this lecture, we're going to use them. Here is a simple example of how we can use our capture list. We have two variables, a and b. They are of double type and they contain these values 10 and 20. But sometimes we want to use things outside the scope of the lambda function inside the lambda function here. And if you set up your lambda function with an empty capture list, suppose you don't have these two guys in, and you try to use a and b like this, you're going to get a compiler error because the body of the lambda function doesn't have access to the outer context here. It can only use things inside the lambda functions or things that you pass to the lambda function here, but it can't directly access things outside the lambda functions. And we can have access to things that are declared and defined outside the lambda function through our capture list. If you look here, we are saying a and b, and this is the syntax we have to capture these two variables, a and b, and have access to them inside our lambda function here. And this is what capture lists are really for, giving you access to things that are declared outside the scope of the lambda function. Because if you really think about it, this lambda function thing we have here is really a type. So it is its own thing that has these behaviors built in so that we can call it and do things, but it doesn't really have direct access to the outside where it was declared. And you have to give it access through the capture mechanism here. Okay, now that you know this, we're going to see different ways we can use the capture mechanism. One thing we can do is capture by value. And if we capture by value, what we're going to have inside the lambda function is going to be a copy. Suppose we have a variable here, which is c. The value is going to be 42, as you see here. We're going to set up a lambda function and capture our c variable by value in this lambda function here. And what we're going to do outside the lambda function, notice the lambda function has a handle so we can call it. We're going to loop 5 times. And at each iteration, we're going to call our lambda function and print the inner value here. But after that, we're going to increment our c variable, and this is going to increment the outer variable here. And what we want to see is that the changes we are doing on the outside here are picked up by the inner value that we have in our lambda function here. And I hate to break it to you, this is going to not be the case because what we have inside the lambda function is a copy of the outside variable here. So what we're going to have is for the outer value to go from 42 all the way to 47, we're going to go 5 times incrementing this little guy, but the thing on the inside is not going to change because it is a copy. The incrementation here is affecting the outside variable here, but it is not affecting the copy we have inside our lambda function. So for all these loops here, we're going to see 42 printed out. And we're going to see this in a minute when we hit Visual Studio Code. Let's say 42 correctly. Excuse my typing here. Okay, so now you know that we can capture by value and you know what this really means. Another thing we can do is capture by reference. And the syntax to do that is to add an ampersand symbol in front of the variable that we capture here. And if we do this and run the same code we run in the last lecture, we're going to see now that the changes we do on the outside are going to be picked up by the inner side of our lambda function because we are capturing by reference. What we have inside our lambda function here is a true reference to the outside variable here. And we're going to see that now the outside and the inside are going to be incrementing together, and we're going to have 43, 42, 44, and things like that printed out on the console. Okay, this is really all I have to share with you in this lecture, showing you how you can use your capture lists, and that you can capture either by value or by reference. We're going to head over to Visual Studio Code and play with this a little more. Okay, here we are in our working folder. The current project is capture lists. We're going to grab our template files pretty quick, and we're going to put them in place. We're going to put them in the current project, and we're going to open this guy in Visual Studio Code by dragging and dropping in place here. And we're going to open our main CPP file, clean it up a little bit, and close the left pane here. What we want to do in here is learn a little more about capture lists, and we're going to put in a piece of code to play with just that. We have two variables, a and 10 here, and we have our Lambda function set up, and let's take out our capture lists so that you can see the compiler error we see if we try to use them as is here. So we have our two variables, and we have a Lambda function set up here, and inside the Lambda function, notice that we are trying to access variables that have been declared on the outside of the Lambda function here. And by default, if we try to do this, we're going to get a compiler error because these two variables don't exist in the scope of the Lambda function here. Let's bring up a terminal and see what Visual Studio Code is saying about this. And it is going to say an enclosing function local variable cannot be referenced in a Lambda body unless it is in the capture list. And you see that this is really descriptive. Okay, we have seen this error, but we want to see what the compiler says about this. We're going to pass this through GCC, and we should get a similar error. It is going to say A is not captured, and it is going to go down here and say B is not captured here. And this is the error. We are trying to use outside variables in our Lambda function, but to really do that, we need to capture A and B. And the syntax to capture our variables is to put them inside our angle brackets here with a comma separated list of the variables that we want to capture. So we're going to say A, comma B, because that's what we want to capture here. And the moment we do that, Visual Studio Code should be happy. It is not happy. I think we need to compile this for it to be happy. So let's do that. And you see now our variables are being captured, and we are summing them up. And we are printing the result of adding them up here by calling the function through a handle we have set up here. Hopefully this is really making sense. Let's build the program again. So let's use the GCC. You're going to see that the build is good. We can clear and run Rooster. We should see A plus B is 30, but the values are getting inside the Lambda function through our capture list. They are not going through the parameter list here. This is really something you need to be aware of. Now that you know how capture lists work, let's see that you can capture either by value or by reference. And we're going to see what that means exactly. I am going to go down here and put in a piece of code to play with capturing by value. Okay, let's do that. We have a variable called C. The value is 42. And we set up a Lambda function which is going to capture C with this syntax here. And this is the default syntax we saw like we did on top here. So we are going to be capturing like this. And if we do this, we're going to be capturing by value. The meaning of that is that what we have inside our Lambda function is not going to be the original value here. It is going to be a copy of what we have there. What we can do here is use this thing in a loop and really prove this. So we're going to loop 5 times from 0 all the way to 4, because this is going to go until I is no longer less than 5. And inside, we're going to print the outer value, which is going to be the C here. After that, we're going to call our Lambda function, which is going to print the inner value in the Lambda function. And we're going to see that the incrementation we do on the outside, which is going to affect the outer value here, is going to be visible inside the Lambda function here. And that's not going to be the case. The change we do here is not going to be picked up by the Lambda function here, because what we have inside is a copy. So what we're going to see is for the outer value to go from 42, 43, 43, 45, and it is going to go until we hit the end of this loop here, but the inside value is not going to change because the change we do in here is not going to affect the copy that we have in our lambda function here. Hopefully this makes sense. And again, if you have a problem, please make sure you ask through the course platform, and I will do the best I can to help you out. For now, we're going to build and run this program. You see the build is good, so let's clear and run Rooster. You're going to see outer value is 43, outer value is 43, outer value is 44, outer value is 45. The outer value is changing, but the inner value is staying at 42, as you see here. Hopefully, this proves that the outer value and the inner value are two different things. But we can even go further and print the addresses of the outer value and the inner value. Let's do that. We're going to add that to our statement here and say the address of this guy. So we're going to say address of outer value, or say address of inner value. We can say it like that to really be descriptive in our terminal here. So we're going to say the address of C, and on the outer value, we're going to add another piece of information and say address of outer value, and we're going to say the address of C. And this is going to pick up the outer value that we have here, and this is going to use the inner value we have in our lambda function here. Let's try and build, and hopefully these two addresses, the inner and outer addresses, are going to be different. That's what we want to see here, and really proving that what we have inside the lambda function is a copy through the capture mechanism. So let's run the program. The build was good. So the outer value, the address is DE4. The inner value, the address is DE0. We are proving that what we have inside our lambda function is really a copy. So this is how you can capture by value, and that's going to make a copy. But sometimes you really want to capture by reference, and we're going to see how you can do that. So we're going to comment out the code to capture by value here. We're going to grab the code and reuse it because that's going to be very similar to what we had before. We're going to say capture by reference. We're going to put in our code, and we're going to change it a tiny bit. What we're going to do is add an ampersand symbol in front of our variable here that we are capturing, and we're going to say ampersand. The moment we do this, what we have inside the lambda function is no longer a copy. It's going to be a true reference to the outer value here. And now the changes we do to our outer value are going to be visible inside the lambda function here. And you're going to see the addresses to be the same. Let's build and really see this. We're going to use GCC to build our program. The build is good. We can clear now and run Rooster. And we're going to see that the outer value, let's make sure we have some spaces after these guys, and let's go up and do that and build again because things are really cramped together and I don't like this. So the build is good. We can clear and run Rooster. So we're going to see the outer value and the inner value are changing together, and the addresses are now the same because we have captured by reference. The inner value and the outer value are referencing the same variable we have outside here. This is really all we set out to do in this lecture. I hope you found it interesting. The main idea was the capture mechanism we have with our lambda functions to capture things outside the context of lambda functions. We can capture by specifying a comma-separated list of the variables that we want to capture, and we have the option to either capture by value by using the variable directly in the capture list like we do here, or by prepending an ampersand symbol here and capture by reference. And you are going to have to choose whichever way you want to capture your variables now that you know about all these options here. We are going to stop here in this lecture. In the next one, we're going to see how we can capture everything from the outside context to the lambda function. Go ahead and finish up here and meet me there. In the last lecture, we saw that we could capture things outside the context of the lambda function. Now we want to see that we can capture everything living outside the context of the lambda function. The syntax to do that is ridiculously simple. If you want to capture everything by value, you just put an equal sign in your Lambda function capture list. And if you do something like this, now you're going to have access to everything outside the scope of the Lambda function. For example, we can access the C variable here from the Lambda function, but if we have any more variables declared outside the scope of the Lambda function, we will have access to them inside our Lambda function here. Again, this is enabled by the syntax that we use here by putting an equal sign inside our Lambda function. Notice that if you use the equal sign like we do here, we're going to be capturing by value. What we have inside the Lambda function is going to be a copy. If you don't want to capture all by value, you can capture all by reference. And again, the syntax is really simple. All you have to do is put an ampersand symbol inside your capture list. The moment you do this, you're going to have access to everything outside the context of your Lambda function, but that's going to be by reference. What you have inside the Lambda function are going to be true references to the outside variables, and you can do pretty nasty things with them because the changes you do inside the Lambda function are going to be visible outside the Lambda function, and any change you do from the outside is also going to be visible inside the Lambda function. So if you do this, make sure this is what you want, and you can use this to your advantage. Okay, now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Okay, here we are in our working folder. The current project is Capture All Lists. We're going to grab our template files pretty quick, and we're going to put them in place. And we're going to open this little guy in Visual Studio Code. Let's do that. We are going to have our folder open. We can open our main CPP file, clean it up like we always do, and we're going to close the left pane here. The first thing we want to do is to capture everything by value. And we're going to put in the code to do that, which should be very easy to understand by now. And again, the syntax to capture everything by value is by putting an equal sign within your capture list. You have to put that within these angle brackets, and that's going to capture everything by value now. Now, if we run the program, we're going to see that C has been captured by value. If we loop around, we're going to see that the outer value is going to change, but the inner value is going to stay the same. This is the same behavior we have seen before by capturing by value. So let's build again. We're going to build with GCC. The build is good. We can clear and bring up a terminal so that we can clear properly. So let's do clear and run Rooster. Now we see that the outer value is changing, but the inner value is not changing. And again, this is classic capturing by value. If you want to capture all by reference, you're going to use the ampersand symbol here. And let's do that. We're going to comment this out, and we're going to take this out and use the code here. We can do that. We're going to go down and put in our code and say that we are capturing by reference. We should say capturing all by reference. And all we have to do to make that work by reference is to put our ampersand symbol within this angle brackets here. And this is going to capture everything by reference. If we run now, we're going to see that the changes we do from the outside are going to be visible from the inside here. Let's build with GCC and see that this is actually the case. The build is good, as you see here. We can clear and run Rooster. We're going to see that the outer value is 42. The outer value is changing and the inner value is changing, as you see in our output here. And this is really how you can capture by reference. Just to play with this, we're going to set up another variable, call it D, and we're going to say it contains a 5. And we can try to print that inside our inner value here, and it is going to work. You're going to see that it has been captured. We can say stdc out inner value. Let's say that it is the D variable we are trying to access here, and we're going to say D, and it is going to be visible inside our Lambda function here because it was captured by reference here. Let's build again. We're going to use GCC to do that. The build is good, we can clear, and if we run Rooster, we should see D printed out multiple times. D, 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 and we are able to access it through the capture mechanism, and we are capturing everything in the context by reference here. This is really all we set out to do in this lecture. I hope you found it interesting. I hate to say it, but this happens to be the last lecture in this chapter on lambda functions. We still have a lot to learn about lambda functions, but unfortunately, we don't really have enough tools to understand that now. But for now, we're going to stop here and learn a little more things about C++. Then we're going to come back and see some crazy things you can really do with lambda functions. I would like to welcome you in this new chapter where we're going to be learning about function templates. Function templates are a mechanism we have in C++ to set up blueprints for functions and have one point of control to set up the function, but the compiler is going to generate the actual function that gets called when it sees the function call. So this is going to solve the problem we had before with function overloads. If you look at the code here, we have multiple overloads for the maximum function. But what we really are doing in the body of these functions is the same. And suppose you have 12 or 13 or 20 overloads of the same function, you're going to be basically repeating the same logic in the bodies of this function. And this code repetition is bad. Function templates are an effort to solve problems like this. The way they work, you set up a blueprint for your function. And this is the syntax to do something like that. You say template type name T here. Don't worry about this syntax. We're going to have a chance to go through it in detail. But if you do things like this, this is going to be a blueprint for your maximum function. And the compiler is going to use this blueprint to generate an actual function when you call this function. And this is going to make things super easy. I realize some of this is really cryptic, so let's head over to the next lecture and let you set up your very first function template. Go ahead and finish up here and meet me there. In this lecture, we're going to set up our very first function template. And again, function templates are a mechanism we have in C++ to avoid code repetition. For example, if you are setting up function overloads. If you look here, we have our max function, and we have multiple overloads for this function. We can call it with int, double, and string view here. But if you look inside, you see that we really are repeating the same logic. And it is even possible to have dozens of overloads if you want to support tons of types for your function. And this code repetition is really bad. Function templates are a mechanism we have in place to avoid things like this. And what you do, you set up a function blueprint using the syntax you see here, and your function template is going to be prefixed with this template type name T thing here. Type name T is going to be in these angle brackets. And then you're going to put the blueprint for your function. T is a placeholder for the types that you use in your function. You see that T is in the return type here. It's in the parameters that we pass to the function. And because it is the same character here, all these things have to be of the same type. The return type, the first parameter, the second parameter, they have to be of the same type. Okay, so once you have your function template set up like this, you're going to implement it like we see down below here. It is nothing complicated. We just set up the prototype for the function on top. And inside we put our implementation. You see here, we have separated this into function declaration and function definition. But inside, you see that it is the same logic we had to compute our maximum between these two parameters that we pass to this function. So how does this work? When the compiler sees you call this max function, for example, as we are doing here, it's going to look at the types that you pass in. And in this case, A and B are of int type. So it is going to replace the T in here for int, and it is going to generate a function in your code. And this really brings up a big point about function templates. Many people think that function templates are actual C++ code. They're not. They're just a blueprint from which the compiler is going to generate the actual function that is called by the compiler, for example, when you issue a call like this. Again, function templates are not real C++ code. They are just a blueprint that the compiler uses to generate your function based on the arguments you pass to the function when you call it. So when we issue the call like we do here, an int version of our maximum function is going to be created. So the compiler is basically going to go in and replace n. Int for t here, the return type is going to be int. The first parameter is going to be int. The second parameter is going to be int. It's going to go in the definition. It's going to do that. And we're going to have an int function. If we issue a call with c and d like we do here in the second line here, then the compiler is going to see that c and d are of double type. So it is going to generate another function from this blueprint here, and it is going to replace in double. Then we're going to have another double function. If we go to the third line here, we're going to do the same. We're going to call it with strings, and it is going to generate a string version of the maximum function here. So what we achieve with function templates is to avoid several overloads for the same function, and we have one point of control in our code. But the compiler is still going to generate these function overloads. But one thing about this is that if a function is not used, for example, if you never call our maximum function with string, then the string version is never going to be created. The compiler is going to generate the overloads that you only call in your C++ program. And this is really all function templates are all about. They give you a mechanism to set up a blueprint for your function, and then the compiler is going to generate actual functions based on what you call in your C++ code. Okay, we have said this, but I want to emphasize this again. Function templates are just blueprints. They are not real C++ code. And when we hit Visual Studio Code in a minute, we're going to see a tool that allows us to see how the compiler instantiates your function templates based on the arguments you call your function with. But keep this in mind, function templates are not real C++ code. The real C++ functions get generated by the compiler when you call your function. And another thing I wanted to point out is that once a function template instance is generated, for example, the int version of our maximum function template, then if it is needed again, the compiler is not going to generate that again. It's going to see if there is one generated already, and it is going to reuse that. Okay, this is really all I have to share about function templates at this point in this chapter. For now, we're going to head over to Visual Studio Code and play with this a little more. Okay, here we are in our working directory. The current project is trying out function templates. We're going to grab our template project. And one thing I should point out here is that our template project has been now updated to have the launch.json file, which is going to allow us to debug our programs. So you should use a template that includes the launch.json file here. That's going to allow us to debug your programs, and we're going to do that in a minute when we have set up the example here. So we're going to grab our template files and put them in place, and we're going to open this little guy in Visual Studio Code by dragging and dropping on top here. This is going to do our job. Then we're going to open up the main CPP file, and I think we should close the left pane here. We don't need it anymore, and we're going to clean this up a little bit. So one thing I want to do is to first do things the bad way. So we're going to set up a max function. Let's call this maximum. And it's going to take int parameters. And we're going to return the maximum between A and B. And the way we do that, we say A greater than B. We are going to use our ternary operator here. We're going to put a question mark. We're going to return A or B. And this is going to be our function. But suppose we need another function that works on doubles. If we put double arguments in here, the compiler is going to insert implicit conversions from double to int. This may seem to work, but suppose you use a parameter type that is not convertible to int. For example, you use a string or something. Let's put in std string here, just for an example. So we're going to say maximum std string A and std string B. And we should make these const references because we're not interested in modifying these strings here. Let's finish the name here. And we're going to say const std string reference A. This is much better. It's going to avoid unnecessary copies of strings. And we're going to say const std string reference B here. Then inside, we're not going to do anything different. We're just going to use the same logic. Okay, let's do that. Suppose you have another function which takes, what should I say, long int. If we need that, we need to copy this function and put that in. Okay, we need to do that, and we're going to change this to long int, and we're going to do the same here, long int, our parameter, and we're going to say the same here. And you see, we are setting up a lot of functions with basically the same thing inside, and this is a lot of code copies. Suppose we have this function maybe 20 times. It is possible, or even worse, the logic in this function is really long, maybe 20 or 30 lines, and we will have to repeat this thing in our code. So the designers of the C++ language saw this problem, and they said, why don't we set up a one point of control where we can set up our logic to do the maximum, and we let the compiler generate actual functions based on the arguments we call our function with. And they came up with function templates, and that's what we're going to see. So we're going to take out all the other functions, and we're going to turn this maximum int function into a function template. The syntax to do that is ridiculously easy. So we're going to say template. This is what you say. You put an angle bracket, and you say type name, and you specify the placeholder for the type in these angle brackets here. This is the syntax you have to use. Then you have to specify your function in terms of this placeholder t. It is going to take the place of the type. So for example, here we want to return int. We're going to change this to t, and the parameters are going to be taken by value t and t. Let's do that. And now we have a legal C++ function template. It is going to take this template here and use it to generate actual C++ functions. So for example, if we go in the main function here and say int result equals maximum, we should say, and say x and y, for example, let's create these variables on top here. So we're going to say int x, and we're going to put in a 5, and we're going to create a y and put in a 7. Why not? Now this function is going to store the result and print it out. Let's do that so that we can see that this actually works. So we're going to say result and say result. This is going to do. And if we build and run this program, we're going to use GCC. You're going to see that the build is going to be good. And build finished successfully. We can run this program like we always do. Let's bring up a terminal and clear a little bit and run Rooster. You're going to see that we're going to see that result now is 7 because that's the maximum. You see, it is working here. So how is this mechanism working here? The compiler is basically looking in the main function here, and it is noticing the call. And it is going to look around and see if it can find a declaration for the maximum function here. It's not going to find it because there is none. Then it's going to look at the function templates it has in here, and it's going to see that it can do a replacement and replacing the types that we are passing in here. So it is going to do that. It is going to take this template and it is going to replace t by int. And then it is going to generate a function that basically looks like what we have here. We're going to copy this and we're going to put this in. The compiler is going to take the first t here. It's going to turn that into an int. It's going to take the second one here. It's going to turn that into an int. It's going to take the third one here and turn that into an int. And we're going to have a function definition for the call here. This is what the compiler is going to do. One thing some of you might be thinking, is there a way to really prove this? And somebody was nice enough to design a tool to let us see this function or template instances generated by the compiler. And I happen to have that opened. It is a web-based tool, so you can use this in your browser. Just go to cppinsights.io, and then we're going to grab the code we had in our main CPP file. We're going to copy it all, and we're going to go back to our browser and remove whatever I had in here because I don't want this anymore. And I'm going to put in my function template. If we want, we can even take this stdc out statement because we don't want all the junk that comes with it. We are just interested in looking at the template instances generated by the compiler. Now that we have the code in here, we're going to see what the compiler generates because of the call we have here. I think I could increase the size of the font here so that you guys can see this. I think this is a little better. Then if you hit this play button here, let's click on it. It's going to do its processing, and then the code generated by the compiler is going to show up to the right here. You see, it has detected that we have called the function template on line 13 here. You see this line is highlighted. And then if you go to the right, we're going to see the functions generated by the compiler. So if you go here, you see that we have an int version of our function template. And another thing I should prove here is that template instances that are not needed are not going to be generated by the compiler. Another way to say this, the compiler is only going to generate the template instances it needs. And again, a template instance is what you have here, the function, the actual function that is callable by the compiler generated from your blueprint. So if, for example, we change the type of our parameters to double, let's do that. Okay, so we changed our types to double. We're going to hit the play button again. You're going to see that now it is going to generate a double function here. You see that here. If we change this, for example, to what can we use? Let's use long int. Like we did in our lecture, we can do that. We can say long int. And if we hit the play button, that's what is going to be generated by the compiler. So hopefully this proves that the compiler is only going to generate the instances that are needed for the calls you do in your C++ program. And this is really function templates are all about. Okay, now that you know this, let's set up a few more examples to see that this really works. So let's change the types of these guys to double. Let's do that. And we're going to play with this a little more in Visual Studio Code. And let's use double literals 5.5 and 7 or 78.7 here. Let's do that, 78.7. And we're going to build this. And one thing I should point out is that template instances are generated when the compiler is doing its job. And then they are going to be put in the binary representation of your source code. So the build is good. As you see here, we can clear and run a rooster. We're going to see that the result is 78. And it is transformed to int because we are assigning to int here. To really get the correct results here, we should use auto type deduction. If we do that, the compiler is going to deduce the type of result here based on the return type of this function, or the function template instance, I should say. Now we're going to change this to auto to do auto type deduction. And if we build again, we should see a double printed out correctly. The build is good, we can clear and run rooster. Now we have the correct value printed out from our function template here. Let's change this to std string. We can do that. So let's include the string library. And we're going to change these two guys to std string. Why not? Std string. X is going to be a string literal. Let's use hello, for example. And for Y, we're going to say std string, and we're going to put in a world here. Okay, this is going to do. And you notice that we don't even have a compiler error. Visual Studio Code is not complaining. The compiler is going to look at the types we call our function with. Then it is going to generate an std string version of this function. And what it is going to do, it's going to replace in T and replace that for std string. We can actually put this thing entirely in CPP Insights. Let's copy this code before we run it so that you can really see what is happening here. We're going to take out whatever we had before. We're going to put in our code, and then we're going to hit the play button here. It's going to generate our thing. We wait for it to do its thing, and if you look here, you see that it has generated std string. This is really a compiler representation of std string. We don't have enough tools to really understand this, but hopefully you can see that it has replaced T with some other type we don't know yet. Std basic string car. It has a few things inside that we don't really know yet. We will have to learn a few more things about this as we progress in the course. But for now, I want to prove to you that the compiler is doing the replacement. You see, T was replaced by this thing here, std basic string, and we have angle brackets, and this entire thing is really std string in the eyes of the compiler. Okay, now that we know this, let's go back to Visual Studio Code and run this. We're going to build with GCC, as we always do. The build is good, we can clear and run Rooster. Going to see that the maximum is world, and this is going to be using the greater than operator, and this is going to compare two strings based on this. And we know that W here comes after H in lexicographical order. So the comparison that is done here is lexicographical for these strings here, or I should say it is comparing things in alphabetical order, in A, B, C, D, E, and things like that. Okay, now hopefully you have a big idea about function templates. They are just blueprints you use to generate actual functions, and this is going to allow you to avoid multiple function overloads as we have seen before. One thing I want you to see is that you have to be sure that the logic you do inside your function is supported by the types that you pass to the function. And I'm going to show you what I mean here. We're going to set up another function template. We're going to say template type name T. We're going to set up another one, pname, and we're going to use T here. You can use this however many times you want. And then we're going to set up a function which is going to do a multiplication. So we're going to say T, that's going to be the return value, and we're going to say multiply, and we're going to multiply two parameters. We're going to say TA and TB, okay? And we're going to put in the logic, and we're going to just return A multiplied by B. This is our multiplication operator in C++. And we can use this function. So for example, we can comment this out, and we can set up two variables. We're going to say int x, and we're going to put in whatever we had before. Let's put in 5, and int y, we're going to say 7. I think this is what we used before. You can really put in whatever you want. And now we're going to call the multiply function template. So what this is going to do is to generate a function template instance, which is going to be of type int. It's going to do a replacement in here and replace T with int. And then we're going to multiply two int parameters that are passed to this function, and we're going to return int. And if we do that, we're going to get 35 printed out. Let's prove this. We're going to use GCC to build. The build is good. We can clear and run Rooster. We get a 35. If we change this to double, it is going to work. So let's change this to double and maybe put in 5.1 and 7.0. Why not? And then we're going to see what we get. We're going to build with GCC. The build is good. We can clear, run Rooster. We get 35.7. This is what we expect. But watch what happens if we try to use the std string types. Okay, I want you to see that. So we're going to enable our std string variables here. And if we try to build, we're going to get a compiler error, but I want you to try and guess why. Why do we have this compiler error? If we look at what GCC is saying here, it is saying in instantiation of our function template required from here and no match for operator multiplication here. And this is the problem. The compiler is going to do what it knows to do. It is going to do a replacement in our function template, and it is going to replace T by std string because that's the type we are using as an argument here. The problem is we can't really multiply two strings. If you try to multiply two strings like we do here, it's not going to make sense. What do you expect to get if you multiply two strings? It doesn't make sense. The compiler doesn't know what to do with this operation. It's going to give you a compiler error. Okay, to really drive this home, let's go back to CPP Insights and put in the code here and see what is generated by the compiler. You should use these tools to your advantage because they really help in understanding what is going on. So let's hit the play button here. I just put in my code and it is going to say compilation failed because we have the same error. CPP Insights needs to compile the code correctly to give you the template instantiations. But here you see that it is basically giving us the same error. Let's try and see the entire thing here and see if we see the real error. and we can't really scroll around with this. I'm having trouble scrolling around here. I can use these buttons, I guess. Okay, so let's see if we see the actual error, and we're not seeing it here. Auto result multiply, error generated. So we're going to get an error if we try to instantiate our template with the types that we are passing in here, which are std string. CPP Insights isn't really helpful here, but hopefully you understand the problem. The problem is if the compiler tries to generate a template instance using std string, multiplying two strings isn't going to make sense. So the compiler is going to give you a compiler error because this is not supported. So the message here is that you should make sure that the template instances generated by the compilers support whatever operations you are doing in the body of your function template. This is the message here. Another thing I want you to see before we close this off, I'm going to take out this problematic line here, and we're going to go back to our maximum function. What I want you to see is that if you pass different types for this function template, you're going to get a compiler error. And what do I mean by that? Let's take out our std string because it's no longer useful for our purposes here. And we're going to just use double and int parameters. Let's use int here, and we make this an int literal. And then we call our maximum function. You see that we have a squiggly line because the function template is forced to use the same type for the return type, the first parameter, and the second parameter here, because the placeholder is the same. So the compiler is supposed to use the same thing for the first argument here, the second argument, and the return type that we get from this maximum function here. But the problem is we are passing in parameters of different types. And this is going to give us a compiler error because the compiler wants to know what to do with the types that you pass in as arguments. And if we look at our problems tab here, Visual Studio Code should give us an error, no match for operator. This is the error we had before. We can try and build again. We're going to get a compiler error again, but this time it's going to be different. It's going to say no instance of function template maximum matches the argument list that we are using here, which is double and int. So this is a problem, but we will see ways around this as we progress in the chapter. But what you should know is that if we set up a function template like this, this is going to enforce for all the types where we will place in T to be the same. If they're not the same, the compiler wants to know how to do its replacement, and it is going to give you a compiler error. Okay, the last thing I want you to see is that we can use the debugger to debug function templates. So let's turn this back to int because we wanted this to compile. So let's take out the decimal point here so that we have proper int literals. And if we compile again, this should compile. Okay, the build is good. Now, what really happens if you try to debug a program with function templates? Are you going to be working on the template instances? Because remember, the function templates are going to generate function template instances with actual types. For example, our template instance here is going to have int because we are passing int as argument here. So how are we exactly going to debug this? Let's try this. We're going to set up a breakpoint here on the call to our maximum function, and we're going to start debugging. We're going to go to our run tab here, and we're going to use the debugging tools that come with GCC. We have seen how to do that in the last chapter, and we're going to start debugging. Let's minimize this guy here so that we have some breathing room, and we're going to run our debugger. Let's maximize this a little bit and push this a little to the left. And we're going to start debugging and see what really happens here. So we hit the green button here. We're going to start debugging. Our code is building now. The build is done. The binary has been passed to the debugger. And now we have hit our breakpoint here. So let's minimize this a little bit so that we have an easier way to see this. We have hit our breakpoint. You see the locals are what we have in the main function, which happens to be to the top of the call stack here. Okay, now we want to jump into the maximum function and see the types that we have inside. So what we want to do here is hit the step into function, and you notice it is going to jump into our function template here, but the locals here are not giving us the types. And this is because this is a function template. It's not going to give you the types because it's not easy to get those here. But if we look at the call stack, you see that we have information about the types of the function that is being called. We are calling int a and int b, and it is going to return int. You see that in the angle brackets here. And again, this is possibly another way to look at what template instances were generated by the compiler. Because we see the function called here is taking int parameters, and it is going to return int. Let's kill our debugger because this is really all we want to see, and change the types to double here. And we're going to see that the function to the top of the call stack is going to be taking double parameters. So let's change this back to 5 point something, 5.5 maybe, 7 and 0.9, why not? And we're going to print our result here. But what we really are interested in is seeing the function template instance generated by the compiler because of this call here. And we can do this through the debugger. This is a little bit convoluted because you have to set up breakpoints and whatever, but it is helpful if you don't want to use things like CPP Insights, as we have seen before. And again, this is also useful because you will need to debug your code if it is using function templates. Let's run this to really prove our point here. The build is going to go through, the binary executable is going to be passed into the debugger, and we're going to hit our breakpoint here. Again, you see our locals are not giving us the types here, but we can use the function call stack to really see this. We have hit the breakpoint here at line 15, so we can step into the call. And if we hit the body of the maximum function here and look at the call stack, we're going to see that the parameters we have in our function call are of double type. And again, this helpfully proves to us that the compiler has actually generated a double function template instance. Okay, since we are debugging, we can actually try and follow this program. Let's hit next so that we can hit the end of this function. We can finish it and hit the main function. By the moment we hit the main function, result is going to be 7.9, which is what we have here, and it is what we're going to print. We can just step over this because we don't want to step into the logics of stdc out. So step over, we're going to print our result, and our debugging session is going to basically end because we have hit the end of the main function. Let's try and use the compiler from Microsoft to see the information it gives us, because these things can be different depending on the compiler and the debugging tools that you are using. We have the luxury to have these two set up here. So all we have to do is switch the tool we want to use here. And this is going to be using the one from Microsoft. If you are not on Windows or you don't want to use the compiler from Microsoft and its debugging tools, you can just use GCC and its debugging tools. Here, I just want you to see different ways to do the same things, and that compilers and debuggers can give us different information. We're going to try and debug with this, so we're going to hit the green button here. Notice that this is going to be using the compiler from Microsoft. If we look at the build output here, you see that we are calling cl.exe. It is what we are using to build our binary. The binary is going to be passed to the debugger, and then we're going to hit the breakpoint here as we know. And then we're going to have our output here. These are our locals. You see in the main function, we don't see the types of our locals. Why is that? I don't know why, but we see the values here in the main function. And if we hit the step into button to jump into our maximum function, A is going to have this value, B is going to have this value, and we look at the template instance, we can see the same information, but we are using a different compiler. This is really how you can debug your code that uses function templates, and this is going to give us a peek into the actual template instance that was generated by our compiler. This is really all I had to share in this lecture, and before I let you go, let's summarize a little bit. Function templates are blueprints. We have seen that the compiler is going to use those to generate actual function template instances. Real function definitions and declarations are going to be created when you call the function with arguments. If the template parameters are of the same type, maybe t and t, then the arguments you call the function with must also match, otherwise you'll get a compiler error. We have seen this. Okay, here we have a point we haven't already covered. Template instances won't always do what you want. A good example is when you call our maximum function with pointers. So let's go back and really see this, because I want this to cover as much as possible about function templates. So let's go back to our code and we're going to modify things a little bit. Okay, so what we're going to do here is take out whatever we have here. We're going to set up int variables x and y. X is going to be 5 as we have seen before, and y is going to be 7. Let's use this. And then we're going to set up 2 pointer variables. We're going to say int pointer px, and we're going to initialize this with the address of x. Nothing sophisticated so far. And we're going to say int py, and we're going to initialize this with the address of y. We can do this. The problem is going to come when we try to call our function here with the pointers. Let's use px and py to call this function, and py. And what this is going to do is to generate a template instance that takes int pointer. This is what the compiler knows to do. We're going to take the types that we pass in here, which happen to be int pointer, and we're going to change the return type to int pointer. We're going to change the first parameter to int pointer, the second parameter to int pointer, and we're going to compute the maximum. If we compute the maximum here, we're going to be comparing pointers. Okay, notice this. And if we try to do that, we might not get what we want, because what we get now depends on the address used to store these guys in memory. Hopefully you can see that. And let's try and debug this program so that you can really see this. We're going to use the tools from G++ or GCC, and we're going to try and debug it. Let's do that. It is going to run through the debugger, and what we're going to have is our terminal here. I think this is not needed anymore, so let's put this to the right here and minimize a little bit. And now you notice that px contains an address and py contains an address. Hopefully you can see that in the body of our template instance, we're going to be comparing these addresses, because we're comparing what we pass by value here and what we pass are these two addresses. So whichever is the maximum in these guys, and I think that's going to be DD4 here, it is the maximum. So whatever is contained in px is going to be considered the maximum. Let's kill this because we have seen this information. So if we have a value in px and that happens to be at a bigger address, it's going to be considered the maximum. Let's see what we print if we run this program. We're going to build with GCC. Let's do that. The build is good. We can clear and run Rooster. Now you see result is some address because we are returning a pointer and printing that out, but we can easily dereference this and get to the value inside this pointer. Let's build again. We can clear and run Rooster. This is going to give us result is 5. And hopefully you can see that this is really bad and not correct. We are trying to compute the maximum between x and y, and we are seeing that the maximum is 5. So how can 5 be the maximum between 5 and 7? The problem is we're not comparing the values here. We are comparing the addresses stored in these pointers because that's what we are passing here. Hopefully you can really see this, and we can prove this again through our debugger. We can run this through the debugger. We're going to hit the breakpoint. Let's minimize this so that we can see our terminal window here, and we're going to move this around a little bit. And now we have hit our breakpoint. If we hit next to jump into the function, you see that what we are really comparing are A and B here, and A contains a much larger address, so it is the pointer that is going to be returned. And if we dereference that, we're going to be dereferencing the pointer that contains this X value. And the message here is that you should be careful that your function templates are really doing what you want. Somebody might do this if they are not careful, just pass in pointer and expect to get the maximum, but the compiler is just going to compare pointer addresses and you're going to get something you probably don't expect. Okay, this is what is meant by template instances won't always do what you want. A good example is when you call our maximum function with pointers, you're going to get a wrong value, possibly. There are tools like CPP Insights, which can show the template instantiations. We have seen that. And again, the arguments passed to a function template must support the operations that you are doing in your function template. We have seen an example of this by setting up a multiplication function template, and we saw that we had a compiler error if we tried to pass std string arguments because we can't multiply two strings. This is really all I had to share in this lecture. I apologize, it turned out to be lengthy, but I really had to put this in one lecture so that I can really show you different sides of the same things. We are going to stop here in this lecture. In the next one, we're going to learn about template type deduction and explicit arguments. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about template type deduction and explicit arguments. What we mean by template type deduction is the mechanism the compiler uses to deduce the type it would use to set up our template instance from the arguments that we pass to our function call here. For example, the compiler is going to look at A and B here in our call to the maximum function, and it is going to notice that they are of int type. And then it is going to say, okay, you are calling your function with int types, and I see that your function template takes 3 replacers in here. So I am going to replace these guys with int. And it is going to guess that from the call that you make here, there's no other mechanism to help the compiler out. This is really what template type deduction is about. And for the first example here, we are passing in int parameters. So int is going to be deduced. For the second function call, we are passing in double parameters. So a double function template instance is going to be generated. For the third call here, we are using std string parameters. So we are going to deduce a template instance that uses std string here. This is what we mean by template type deduction. But we have seen that automatic template type deduction can really have problems, especially if you pass parameters of different types. For example, if we call our maximum function here with A and C, which happen to be int and double type, then we're going to have a problem because this function template can't handle parameters with different types. Because the replacer is the same, the compiler is going to enforce that all the template arguments are of the same type. And the template arguments are going to be what you pass in here. So A and B must be the same. If they happen to be not the same, for example, int and double, you're going to get a compiler error. Now we're going to see that we can use explicit template arguments. And again, I want to make it very clear the difference between a template parameter and a template argument. A template parameter is what you have in your function declaration or definition. So what we have in our function setup here are template parameters. TA here and TB are template parameters. But what we have when we call our function template is going to be template arguments. For example, C and D here are template arguments, and we're going to be using this terminology in this chapter and many more chapters to come in this course. Make sure this is super clear. So what we're going to look at is using explicit template arguments. And what this means is a mechanism through which you can force the compiler to use some type to generate your template instance. And the syntax to do this is really simple. It is what we have here. We say maximum and we put the type we want to use to generate our template instance in angle brackets like we see here. So this is going to use double. So this is going to explicitly tell the compiler we want the double version called. And it's going to generate that, and that's what is going to be called by this call we have here. A good benefit with this is that now this is going to support template arguments of different types. So if we make the call like this, the compiler is going to see that, we are calling with int and double types because A is int and C is double. But it's going to see that you want the double template instance generated. Now the compiler will have the possibility to do implicit conversions from other types to double. And if this implicit conversion fails, then we're going to get a compiler error. So if you look here, for example, This is the example for that. We are passing in A and E, and A is int and E is an std string. We cannot do an implicit conversion from std string to double, so this is going to give us a compiler error. And this is really all template type deduction and explicit arguments are about. We can use these things to really make our code easier. Now that you have this understood, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working directory. The current project is template type deductions and explicit arguments. We're going to grab our template files pretty quick and put them in place. And after that, we're going to open this in Visual Studio Code. Let's drag and drop on top of Visual Studio Code here. This is going to open our folder, and we can open our main CPP file and set up our function template. Let's clean this up a little bit, and we're going to set up our function template. Let's type this out just to practice. So we're going to say template, and we're going to say type name, and we're going to say T. And if you want, you can put this on a single line, but I prefer to put this on separate lines. But let's show you that. So we're going to say T here, and we're going to say maximum, and we're going to say the parameters. They are going to be of type T, and we can pass them by value just for now. And after this, we're going to go in the body of our function template, and then we can return whichever parameter is the maximum. We're going to say A greater than B here. We're going to use our ternary operator. And if A is greater, we're going to return A. If B is greater, we're going to return B. And this is our function here. Okay, now that this function is set up, let's set up a few variables to really play with it. So we're going to include the string library because we're going to be using it a little bit. And we're going to go down in the main function and put in our few variables. We have A through F here. A and B are int, C and D are of type double, and E and F are of type std string. The first thing we can do, we can say auto max, and we can assign whichever is the maximum between A and B. And once we do this, we're going to have that maximum stored in max here. But what I want you to see is what the compiler does when it sees the code like this. The compiler has no other outside help to know the function template instance it should really generate. It is going to look at the types we have here, A and B. It's going to see that they are of type int. It's going to see that it can use the function template we have here, and it's going to use that and generate a template instance that is going to take int, and it is going to call it to get our maximum here. Again, we can prove this through the debugger. We're going to set up a breakpoint. We're going to go to our run tab here, and we're going to run this through our debugger. We're going to build our thing, and when we hit the main function, you're going to see that A is 10, B is 23, which is what we have here. C, D, we have our values N, and std string, because it is a compound type or a custom type, we can expand on this and really see more information about this. But we don't have enough tools to really understand this by now, so we're going to use this as a wrapper on our string information here. Now, we want to call the maximum function and see what was generated by the compiler. And we can step into this function because we have hit the breakpoint by now. So if we hit step into, we're going to step into this function, and we're going to see that it is an int function instance that was generated. This is enough for our purposes. If we change our call here to use C and D, we're going to generate a double instance. So let's do that. We're going to generate a double instance, and if we print this out, we're going to see this printed out. But we can use the debugger to really prove this, not that we know how to use it. We don't have to look through the terminal output window, but you can do that if you want. You can set up stdc out and print max here. You're going to see it printed out. So let's run our debugger. We're going to see the template instance that was generated through the debugger. We're going to hit the breakpoint at line 17 here. If we step inside, we're going to see the local variables for our function here, A and B, and we're going to have the maximum function to the top of the call stack, and you're going to see that it is a double instance for our function template here. Okay, this is what we mean by template type deduction. It is the default mechanism that the compiler uses to know which template instance to generate from your function calls. But as we have seen in the last lecture, this can be problematic. One way this can be bad is if you pass different types to the maximum function here. Let's pass in A and C, for example, or A and D. This is going to work equally well. You see that we get a compiler error because the compiler now, it sees that we are calling with different types, but the template parameters here are really of the same type. They should be of the same type because T is going to be replaced for a single type. So the call we do here is going to fail. And if we run this through the compiler again, let's do that. We're going to use GCC. We're going to get a compiler error, and it is going to say deduce conflicting types for parameter T, int and double. So it can't really know which one you want. You want int or double. The compiler doesn't know, and it is going to give us a compiler error. But now we're going to see a mechanism we can use to make this work. And that's going to be explicit template arguments. Okay, what we can do to do this, we can go down and put in our call. We're going to say auto and say result or max. We can call this however we want. We're going to say the name of the function, and we're going to specify the template type that we want generated for our function template here. So if we do something like this with double inside angle brackets here, we're going to be basically telling the compiler, please generate a double template instance for this call we are doing here. So if we pass in C and D, for example, this is going to give us what we want, and we can print this out if we want. So let's say max. Okay, this is going to work. If we build, let's build with GCC. Let's use that. The build is going to be good because we are passing in double arguments. And if we run this, we should see our maximum. Let's bring up a terminal window and Visual Studio Code here so that we can use that to see things running. We're going to clear and run Rooster. You see that we have our maximum here. But using explicit template arguments like we are doing here is going to allow us to even pass different types for our template arguments. And for example, now we can change the first argument here to be A, which is going to be an int, and we're going to leave the second one to be D, which is of type double. Now the compiler is going to see that we're going to generate a template instance of type double, and it is going to know that it can do implicit conversions for the arguments we pass in here. So this is going to work if we pass an argument that is implicitly convertible to the type we passed in the angle brackets here. And let's debug this again to show you that we're going to generate a double template instance that is going to be called and give us the maximum that we print here. So we can run our debugger by hitting the green run button here. Let's minimize this so that we can see our terminal window, and it is down here. Let's grab it and put it to the left so that we can really see things printed out as we debug. We have hit the breakpoint here, and we have our local variables. You can look at this if you want. It is basically what we have in the main function here, but what we want is to step into this maximum function, and we're going to see the template instance that was generated. You see that it is of double type here. Okay, hopefully now you can see that even if we passed different values for our template arguments, I should say different types, because A is of type int and D is of type double, but we're not getting a compiler error. The compiler is going to insert implicit conversions from whatever arguments we pass here to the explicit template argument that we specified here. Again, the explicit template argument like we are doing here using the syntax with angle brackets and putting in our type is going to tell the compiler, please use this type and replace that for T in our function template here and generate a template instance we can call to service this call here. And we're going to do implicit conversions basically from int to double because that's what we want. Then D is going to be of double type. We're not going to do any implicit conversion. Then we're going to call this function. We're going to return a double from int because that's our template instance, and we're going to print that out here. This is what is happening, and we can prove that a double instance was generated through our call stack here. We see the maximum function is taking in double parameters, and it's going to return double. as our explicit template argument here. This is the syntax that GCC is using, but we know now that it is a double template instance for our function call here. Okay, if you're not happy with what we are seeing with the debugger, you can also use CPP Insights to really prove this. Let's open this up. We're going to say CPP Insights. Let's do that, and we're going to have it open here. Okay, we're going to erase whatever we had in here, and we're going to put in another piece of code. We have our maximum function, I should say template function or function template, and we have our call here, and it is passing different types, A and D. Remember the last time we did something like this by passing in different types for the template argument. This guy failed. It couldn't really generate a function template instance because the template parameters we have on top here specify that these guys should be of the same type. But now we are able to use different types as arguments because we have an explicit argument specified. Let's run this and see the template instance that is generated, and you can see that it is of double type. We basically replaced every instance of T here with double, and this function is going to be called to service the call we are making here. Okay, this is really all we set out to do in this lecture. I hope you found it interesting. The main message was template type deduction, a default mechanism C++ uses to know which template instances to generate from your function calls. But if the defaults aren't working for you, you can use explicit template arguments to specify the template instance you want generated. We are going to stop here in this lecture. In the next one, we're going to see how we can pass template parameters by reference. Go ahead and finish up here and meet me there. In this lecture, we're going to show you that you can pass your template type parameters by reference. And we're going to look at a simple example to really drive this home. What we have seen so far is that we can do things like this and specify our T like this. And this is going to generate a template instance that passes arguments by value. For example, if we pass in double A and double B here for our maximum, we're going to generate a template instance which takes double as parameters and returns the double here. And this is going to be doing things by value. Okay, this is what I want you to focus on right now. It is that this is going to do things by value. So if we go in our function here and compute the maximum, you're going to see that the addresses we have on the outside are going to be different from the addresses we have on the inside here if we try to print them out. But you can also pass your template parameters by reference. And the syntax to do that is ridiculously easy. You just use this like you would use any reference. We say const t reference here, and this is going to just replace in whatever type that you pass when you call the function here. For example, here we are passing in double arguments. So this is going to deduce a double template instance, which basically says const double reference maximum, const double reference A, and const double reference B. And this is going to be the function that is called. So this is going to really do things by reference. And the values we have inside our function template body here are going to be true references to the values we have on the outside. If we happen to do any modification inside the body of the function, the modification is going to be visible on the outside. What we're going to be doing in this lecture is just printing the addresses here, and we're going to see that they are the same here on the outside and inside the body of our function template here. Okay, this is what we want to really play with in this lecture. But before we head over to Visual Studio Code, I want to show you that you can confuse your compiler if you are not careful. If you set up these two function templates you see here, they are going to be overloads, and we can use function overloads with templates. But for now, we're just going to focus on the parameters that we are passing in here. The first one is taking things by volume, and the second one is taking things by reference, as we see here. And if we issue a call like this, we're going to have the same problem we have seen with function overloads before. This is not going to know whether you are calling by value or by reference, and this is going to cause a compiler error. I really want you to be aware of this. Okay, now that you know this, we're going to head over to Visual Studio Code and really play with this a little more. Okay, here we are in our working folder. The current project is template parameters by reference. We're going to grab our template files and put them in place. So let's do that. And we are going to open this little guy in Visual Studio Code by dragging and dropping here. The folder is going to open up. We're going to open it and we're going to close the left pane here and clean up our main file here. And we are going to put in our function template. One thing I want you to see in this lecture is that it is possible to separate these things into function declaration and function definition. Let's just try and do that here so that you can really see this. And then you're going to have to choose what you like a little more. So let's grab our function header here and use that as our prototype. We're going to put that in front of the main function, and that's going to be our declaration. And if we go down after the main function here, what we have is our definition. This could work, and this is going to generate template instances for the calls we do in the main function here. Okay, now that we have this, we can head in the main function and really play with the function template here. We're going to set up two double parameters, and we're going to call the function. For example, we say auto result, and we're going to call the maximum function, and we're going to pass in A and B. This is going to do default template type deduction, and it is going to generate a double function template instance here. But what we really want to prove is that this is going to pass things by value. And one way we have to prove this is to print the addresses both on the outside and on the inside of the function here. You see, we are already doing that in our function template body. We are going to print the address of A. So we can really grab this and reuse this stdc out statement. And we are going to change it to say out here. And we're going to print the address of A. Let's grab this again and use this after the function call. And what we expect to see is some address on the outside. So for example, we may have something like 0x and 111 ABC, which is some hex number here. And that's the same thing we're going to have on the outside, because the value we have before the function call and the value we have after the function call are going to be living at the same address. But what we have inside the function body is going to be a copy. So it's going to live at some other address, for example, let's say DA. And the main point here is that what we have on the outside is going to be different from what we have on the inside. And hopefully this is going to prove that we are passing by value. So let's print out our maximum here and see the addresses printed out. We're going to build with GCC, and we're going to build successfully. We can bring up a terminal to play with this a little more. We can clear and run Rooster. We're going to see that the address on the outside ends in DD8, and the address on the outside ends with DD8 after the function call. But inside, you see that we have a different address. And this is going to tell us that we are passing by value, and what we have inside the body of the function is basically a copy. Again, I don't expect you to see the same addresses as me here, because your operating system is going to set up the addresses however it wants. The main point here is that the addresses you see on the outside are going to be different from the addresses you see on the inside here. And this proves that we are passing by value. But what if you don't really want to pass by value and make your function template work by reference? Well, we can do that. We can change our function here to do things by reference, and all we have to do is use t-reference like this. Okay, and when we start using references, we really need to be careful and make sure people don't modify things without our knowledge. And a good practice is to mark your things as const references. So we're going to do that. And we are going to do the same in our function definition. So we're going to change this to const t-reference. Let's do that. And I'd say const t-reference for the first parameter here. And say the same for the second parameter here. And this should be it. We shouldn't be able to use this reference to modify the data inside the body of the function, and our function is a little safer. But what the compiler is going to do is really what it's been doing all along. It's going to look at the arguments that we pass to the function call here. It's going to see that it is double, and it's going to do default template type deduction. So it's going to generate a double template instance for the function template here, and it's going to replace in double, and we're going to have const double reference maximum, const double reference A, const double reference B. And we can prove this by going into CPP Insights. I think we can do that. So we are here in CPP Insights. We can take out whatever we had. We're going to put in new code here, and we can hit the run button to generate our instances. And here we have our template instance here generated. You see that it is going to generate a double version of our function template here. And this is what we have. So const double reference maximum, and it is going to put in a double explicit argument here, but this is business of the compiler. What we really care about is that it generated a double template instance for our function template here. Now, if we run this, it is going to be passing parameters by reference, and what we have on the inside should have the same address as what we have on the outside here. So to really drive this home, we should change our address to ABC to comply with what we have on the outside here. We can try and build our program. We're going to use GCC to do that. The build is going to be good. We're going to clear. And if we run Rooster, we should see the addresses being the same. Out DE0, in DE0, and out DE0. And you see now we are passing our parameters by reference. And if you want to set up a function template that passes template parameters by reference, this is how you can do this. And I think we can also try and debug this and see if we can see any more information on how this works. We're going to hit our run tab here, and we're going to hit the green button to start debugging this program. We're going to be using the debugging tools from GCC, and we see our local variables here. We have hit the breakpoint, and we have the main function to the top of the call stack. This is what we have here. And if we try and step into the maximum function, we're going to see that the template instance now is using const double references. And this is the template instance that was generated. I think this is all we can really see here. And let's stop this and show you one last thing. What I'm going to show you is that you can't really have the function template that passes by value and the other one passing by reference. If you do that, you're going to have problems when you issue the code like this because the compiler is going to be confused. Let's change the second one here to pass by value. So we're going to remove the const reference here. I think it's going to do. Let's do that pretty quick. We'll remove the const and the reference. We remove the const and the reference here, and we use this guy as our function prototype in front of the main function here. And how can we say that? We're going to go on top here and say that. Okay, we're going to put our semicolon, and this is going to be our declaration. But the moment we do this, you see that our compiler is going to be confused because we have two possible candidates for the call here. It can either be by value or by reference. And if we try to build this program, we're going to get a compiler error, and it is basically going to be saying what is wrong here. So it's going to say call overloaded maximum double ambiguous because we have two candidates again, one by reference, one by value, and this call can be surfaced by both of these candidates here. So the compiler is going to give us a compiler error, and we have no choice but to use either of these two, but we can't have them all in our code. And for example, if we take out the one by value here and leave in the one by reference, so let's comment this out again. If we build, we're going to build. You see the build is good, and we're going to print our data. However, we have it in our code. We see the addresses are the same. And another thing I don't think I really proved to you is that we are passing by const reference here. So the template instance that is going to be generated is going to be passing by const double reference because we are passing in double parameters. But because of this const in front of our arguments here, we want to be able to modify the data referenced by this name here. If we go inside, for example, and say ++a, try to modify a in any way through this reference, we're going to get a compiler error. Let's build again, and we're going to see that. And build finished with an error. And it is saying increment of read only reference A, because we are passing by const reference here. So you should really remember this, even if we are doing things in the context of function templates. This is really all we set out to do in this lecture, showing you that you can set up function templates that take parameters by reference, and contrasting this with passing by value and seeing the differences between these two things. We're going to stop here in this lecture. In the next one, we're going to learn about template specialization. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about template specialization. And this is a feature we have in C++ to bypass the default mechanism of how function templates work in C++. Okay, let's make myself super clear. Here we have a simple function template we have seen 1,000 times by now. It is the maximum function, and it is going to compute the maximum between A and B here, and it is going to return that. It is a function template, so if we pass in A and B, which are of type int, we're going to generate an int instance of the template here. If we pass in C and D of double type, we're going to generate a double instance of the function template here. If we pass in std string parameters, we're going to generate an std string instance of this template here. And this is going to basically be comparing the parameters we pass. So we're basically going to say if A is greater than B, then return A. If A is not greater than B, then return B. Okay, that's going to work if what we're doing is what we have here. But the moment we pass something like what we have here, const char pointers, then we're going to have a problem, because we're going to be calling our function template with const char pointer parameters. The default mechanism is going to deduce a template instance that works on const char pointer arguments here. And what we're going to be comparing now are going to be pointers to the string rather than the string data itself. And hopefully you can see that this is going to be a problem. Template specialization is a mechanism we have to tell the compiler for a template function, if I pass you this type, please don't do the default thing you do of replacing in the argument type for the template parameter. Instead, use the implementation that I am going to give you. And you tell that to the compiler using the syntax we have here. You put a template keyword here, you put an empty pair of angle brackets, and then you specify your function the way you want it. You see, it's going to return a const char pointer. The function name is maximum, which should be the same as the function template here. It's going to be specialized for const char pointer. So we specify an explicit template argument here, and then we pass our parameters, which are also of const char pointer. And when we do this, then we can head in the body of the function and do the comparison however we want. Okay, so how do we do this comparison here? Here is a simple implementation of the function template we just saw on the previous slide. You see that it really is the same thing. We have the template keyword, we have our angle brackets, and we have the function header here. It's going to return const char pointer. It's going to be called maximum, and an explicit template argument is specified within these angle brackets. And then we have our parameters. What is really important about this function is that it's not going to do the comparison we've been doing all along. It's going to use a built-in function in the C++ standard library, which is specialized for comparing C strings. Okay, if we come at CPP reference here and look at a function called strcmp, we have seen this before, I guess. It is going to compare two null terminated byte strings lexicographically. And you see, this is really what we want. We have two const char pointers. One is going to be the first parameter, the other is going to be the second parameter. We're going to compare them and look at the return value we get from this function. We're going to get a negative return value if the first parameter comes before the second parameter in lexicographical order. We're going to get a 0 if they are equal, and we're going to get a positive value if the first parameter comes after the second parameter in lexicographical order. So we're going to use this information here and compare our two C strings here and return something in Visual Studio Code. Okay, so this is the function here. It's going to be using the logic from strcmp. And notice what we return. We're going to return whichever string compares greater to the other. So we're going to do strcmp. We're going to pass in our two arguments here, and we're going to say if this returns something greater than 0, return A, because in that case A is greater than B lexicographically. This is the comparison we want to do here. And otherwise you're going to return B, and this is going to compare our strings and not compare pointers directly, which is what we are trying to avoid here. And you see that template specialization is really helping out here. Now, if we have this in and the compiler sees a call like this, it's not going to compare pointers. It's going to use the template specialization because the compiler knows that this is a better fit for the call that we are doing here because we are passing const char pointers. This is how template specialization works, and it can really come in handy if you are doing things that work with pointers. We are going to head over to Visual Studio Code and play with this a little more. Okay, here we are in our working folder. The current project is template specialization. We're going to grab our template files. We're going to put them in place, and we're going to open this in Visual Studio Code by dragging and dropping on top of Visual Studio Code here. This is going to open our project, and we're going to clean it up a little bit. And we're going to close the left pane here. We don't need it anymore. The first thing we're going to do is to put in our function template. The same thing we have been doing for a gazillion times by now. The maximum function is going to return whichever is greater between A and B, and it is doing this by value. After that, we're going to head over in the main function and set up a piece of code to really play with us. We're going to set up a few variables, and we're going to call our functions. So we're going to say maximum A and B. This is going to return the maximum between A and B. The compiler is going to deduce that the template instance should be of int type. So it's going to generate that and call it. It's going to give us the return value here. We can print it out and see it. And we're going to basically do the same for double type and string types here, and you're going to see that this is going to work just fine. So let's build this. We're going to use GCC to do that. The build is good. We can clear and bring up a terminal to run this and really see the output here. We can clear and run Rooster. You see max int is 23 because that's what we have here. Max double 34, and that's what we have here, and we called max double to be of int type. We should use auto type deduction here to avoid these mistakes because the compiler can do this better than us. That's what we're going to do, and we're going to deduce max str here, and we're going to build again. Let's build with GCC because that's my favorite compiler. I'm going to clear and run Rooster. Now we have correct output. We have 23, which is the maximum between A and B. We have 34.7, which was deduced to be of type double here. And then we have the maximum string, which happens to be world here. Again, when comparing strings, the default is going to compare them lexicographically. And what that means, the one that comes after the other in alphabetical order is going to be greater. By that logic, world is greater than hello, and it is what we are seeing printed out here. Okay, this is working just fine. But what if we use const char pointers and try to call our maximum function template? And by that I mean doing something like this. We have two variables, g and h, which are of type const char pointer, so they are C strings. They are going to be null terminated because we are initializing them with a string literal, and we are comparing them here. We are saying maximum g and h, and we're going to print whichever is the maximum after we return that from the function. When the compiler sees the call like this, it's going to do what it knows to do. It's going to replace in const char pointer in our function template here. So it's going to return const char pointer. It's going to pass the parameters as const char pointers. And we're going to be comparing these pointers here. And we're going to return whichever pointer is greater. Again, here you must be noticing the problem. We're going to return whichever pointer is greater, and we're not going to be returning the actual string data. We're going to be returning just the address. And this can be really wrong because if the addresses happen to be messed up, we're going to get the wrong output. So let's try and prove this again. For that, I am going to comment out what we had on top here because this could mess things up a little bit. So I'm going to comment all this out, and I am going to debug this. So we're going to look at this line here, and I think we should say const car pointer result and say equals maximum g and h, and I printed the result here. This is going to make it easier to step into this function without the noise from stdc out here. So we're going to set up our breakpoint here. We're going to hit our run tab, and we're going to debug this program, and we're going to hit this breakpoint here. Let's see the types that we have inside our function call. So now that we are here, we're going to see that our locals are g and h, and they contain our string. If we go inside, we're going to see that g is really a pointer to the first element in our string here, and it contains w here, which is what we have here, and h is going to be a pointer to a. That's what we have here. Okay. And result is going to contain some junk data because it's not initialized yet. But we can step into this function and see things happening. A, again, is an address, and B is an address. You see that the debugger is really smart. It's noticing that this is a pointer to a string, and it's going to show us the string here. But what we compare are these two addresses. And you see that B lives in a larger address. It lives at address that ends in 55, and A lives at the address that ends in 50. So if we really execute this function, we're going to return the pointer to B, but you see that B is not really the greater string. And this is really something bad. You should be aware of this. This is what the compiler is doing by default, and it is going to give us a result that is not correct. Let's close this and see a way we can solve this problem, and we can use template specialization for this. What we really need is a way to compare C strings and not compare pointers like we are doing here. We're going to do that using a template specialization, and the syntax for this to work, you say template, and you specify an empty pair of angle brackets, and then you specify whatever function you want to use. So we're going to go down here and specify that we want to return const car pointer. The function is going to be called maximum. We're going to specify an explicit template argument, which is of const car pointer, because we want this template instance to work for const car pointers. So once we have this in, we're going to specify our parameters. We're going to say const car pointer A and const car pointer B, and we're going to head into the body of our function template here. Now, we have our two parameters, and we're going to compare them as if they were const car strings. And we have seen that we have a built-in facility from the C++ standard library. It is this strcmp function. We can use it to compare two strings, and we're going to use the logic that we have here. So if the first parameter is less than the second parameter, I am talking in lexicographical order, we're going to return something negative. If they are equal, lexicographically, we're going to return 0. And if the first parameter is greater than the second parameter lexicographically, we're going to return a positive value. So let's transform this logic into a ternary operator. We're going to say return std_str_cmp. We can say that. And to have access to this function, we're going to need to include C-string. Let's do that. We're going to include the C-string library. And now we can say this, and we're going to pass in A and B. And we're going to ask ourselves, is this greater than 0? Okay, if it's greater than 0, then the first parameter is greater than the second parameter lexicographically. So we're going to return A. If it's not the case, we're going to return B. This is our ternary operator here, and it is going to work. Now that we have this in, the compiler is going to know we have a template specialization for const car pointer. If we call the function like we did here, calling the maximum function, the compiler is not going to use this function template we have on top here. It's going to see that this template specialization is better for the const car pointer type that we are passing here. And now if we try to build and run the program, the build is going to be good. If we clear and run Rooster, we're going to see that now the maximum is wild. Let's see what we see if we don't have this specialization. And we're going to comment this out because I don't think I really showed you. We're going to build again. And again, if we do this, this function template is going to be used, and you know that it is going to deduce a function that compares pointers directly, and that's going to be really bad. We can build this with GCC and really see what we get as output. We can clear and run rooster. Now you see that we are saying animal is the maximum between these two guys, but that's not true. Animal is less than wild in lexicographical order. We need a way to really compare C strings properly. And our template specialization is really doing that using the stdcrmp function, and it is working pretty well. This is really all template specialization is all about. You're going to do this if the default function template you have is really not working according to your needs for the type that you want to use for this. And use this to your advantage because it's available to you and now you know how to use this. The syntax is really simple. You say template and you say angle brackets, and then you specify whichever implementation you want for your specific type. For example, here our specific type for which we want to specify this function template is const car pointer. You specify that as an explicit template argument, and then you specify your return value, your parameters, and you do whatever logic you need to do things right in the body of this template specialization here. I would like to welcome you in this new chapter where we're going to be learning about concepts. Concepts are a mechanism we can use to set up constraints or restrictions on the template parameters in our function templates. For example, we can use this technique to say that we want our function to be only called with integers, and if you call it with something that isn't an integer, it's going to give you a compiler error. One thing I should emphasize is that concepts are one of the big 4 features in C++20, so we're going to be learning about this in this chapter. We have just said that we use them to place constraints on our template parameters, but we saw that we could do something like that in the last chapter where we could use type traits and static asserts. For example, if you look at the function here, it's going to print a number, but we have a requirement for this number to be an integral type through the static assert that we have here. We're going to see that we can do something really similar with concepts, but it's going to be much cleaner in that the logic to enforce our constraints is not going to be in the function body. It's going to be somewhat in the function declaration in the constraints that we put on the template parameter here. We're going to see specific syntaxes of how you can do this starting in the next lecture. There are 2 sides to concepts in C++. There are standard built-in concepts that come with the C++ programming language. But if for some reason these happen not to be enough, you can build your own, and we're going to see how we can do that later in this chapter. Here are a few examples of concepts you can use in your C++ program. You can use the integral concepts to enforce that your parameters be integrals. You can use the floating point concept to enforce that your template parameters be of floating point type. You can do all kinds of crazy things. Okay, concepts are really cool and they are going to make your function templates much safer to work with. We are going to stop here in this lecture and show you how you can use concepts starting in the next lecture. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about concepts. Again, concepts are a mechanism we have in place in C++20 to place constraints on our function templates. For example, we can use concepts to specify that we want our function template to only be called with integers or doubles or strings or whatever, and when somebody violates our concept, they're going to get a compiler error. In this lecture, I am going to show you how you can set up your concept and different syntaxes you can use and how we can understand them. But before we do that, please note that there are 2 sides to concepts. There are concepts that are standard and built into the C++ standard library, and those are ready to use, and these are what we're going to be using in this lecture. But know that you can also build your own concepts and use them to do whatever it is you want to do. Here are a few examples of built-in concepts we can use from the C++ standard library. We have, for example, a concept we can use to enforce that people call our functions only with integral types. If they violate this, they're going to get a compiler error. We can also enforce for our template parameters to be floating point. We can do all kinds of crazy things. Okay, now that you know this, let's see how we can set up a concept on our function templates. And this is the first syntax we're going to look at. All you really have to do is to put in your template declaration like we have been doing all along. You also have to add in the requires keyword here. After the requires keyword, you're going to specify your concept and specify your template parameter in angle brackets here. When you have this thing in front of your function template like we have here, the function template can only work right if the concept in here is satisfied. And this concept in this case is going to be satisfied if somebody tries to call this function template only with integral types. If they violate that, again, they are going to get a compiler error. Okay, once we have this concept set up, we can look at a piece of code that tries to use it and try to guess what is going to happen. Here is a piece of code we would set up in the main function and try to call our function template. We have two variables of car type. We know that car is an integral type. So if we issue a call like this call is going to work. The template instance is going to be generated and it's going to be called and give us the results that we can print here. This is right. On the second piece of code here, we have two variables of type int. We're going to call our function template with int. And this is also an integral type. Int is an integral type, so this is going to generate our function template instance, and we're going to call it and get the results that we print here. And if we try to call our function template with double types, the concept is not going to be satisfied and we're going to get some kind of error and our function template instance is not going to be generated. This is really how you can use concepts to force some rules on users of your function templates, if I can say it like that. We have been able to do something like this using type traits and static asserts in the last chapter, but concepts are much cleaner in that they are kind of built into the signature of your function. You don't have to go in the body of your function and set up static asserts. The function is already supporting concepts when you declare and define it, and this is really cool. Okay, this is our first syntax we can use to set up concepts for our function templates, using the requires clause after our template declaration and following that with whatever concept we want to enforce on our function template here. Please note that you can also use type traits directly in the requires clause here, and this is going to work. And this really says that all you really have to put after the requires clause is an expression that can be evaluated at compile time but also results in a Boolean value. Once you satisfy these few requirements, you can really set up your concept however you want. You just have to be careful that the expression can be evaluated at compile time and that it evaluates to a Boolean value. And when the expression evaluates to true, the concept is going to succeed. If the expression evaluates to false, you're going to get a compiler error because the concept is not satisfied. This is how these things work. Now that we have seen the first syntax, I think it is big time we looked at the second way you can set up concepts, and that's going to be in your template declaration. You're going to say template, put in your angle brackets, and inside, instead of saying type name T like we have been doing all along, you just specify your concept directly and say the template parameter like this. Once you do this, this concept is going to be enforced on this function template here. This is just another syntax to really do the same thing. We also have a third syntax we can use if we use auto to set up our function templates. And the way this works is to just add your concept in front of the auto keyword. And once you do this, the compiler is going to enforce for the first parameter and the second parameter to this function to satisfy the integral concepts. So if you have to use auto to set up function templates, this is how you can use concepts to constrain ways in which people use your function. We still have another way we can use concepts in C++, and this is how you do it. You specify your template declaration like we have been doing all along. You specify your function template But after the parameter list, as we see here, you're going to put your requires clause, and you can put that in this place here, and it is going to work. I realize these are many syntaxes to process for the first time, but some of these syntaxes are going to work better in some situations, and they are there just to make it flexible for you to use concepts in your C++ code. Okay, now that we have seen different ways we can set up concepts for our function templates, I think it is big time we headed over to Visual Studio Code and tried them out. Okay, here we are in our working folder. The current chapter is concepts. The current lecture is using concepts. We're going to grab our template files. We are going to put them in place. And we are going to open this thing in Visual Studio Code by dragging and dropping on top of Visual Studio Code here. We do that. This is going to open our folder. We're going to open up our main CPP file and close the sidebar here. And we're going to clean things up a little bit. And we're going to set up our function template, which is going to add 2 numbers. We already know how to do that. So we're going to say template type name, and it's going to have a template parameter of t. Then we're going to set up the function like we have been doing all along. We're going to say add. We're going to say TA and TB, and this is going to return the sum of A and B. Once you have the function in, we can go in the main function and set up code that would call this function. And if we try to compile this program, it is going to work now because we are not placing any constraints on this function template here. Let's try to build with GCC like we have been doing all along. You see, it is going to build. Okay, you see the build is good, build finished successfully. And if we want, we can run this application and it is going to print result A, result B. Let's take this out because we haven't done this yet. But it's not going to print result C, but if we want, we can really print it. It's going to work. So let's put that in and we're going to say result C and print result C here and build again. Let's build now to take this into account. Build is good. We can bring up a terminal to try this out and we can clear and run Rooster. Now you see result A is 30 because that's the sum of A and B here. Result B should be 16, which is what we have. Result C is 13, which is what we should get by adding these 2 double variables. Now, we want to constrain this function to only work if somebody passes integral types in. When we put that constraint in place, it is going to work if we add up 2 character variables because they are integral types. It's going to work if we add up 2 integer variables because they are integral types. But once we hit this guy here with double variables, we should get a compiler error because the constraint is not satisfied. Let's do that. We're going to comment the double thing first because we want to really isolate it and see the compiler error that we get. And we're going to add a constraint to our function template using concepts. Okay, if you want to use concepts in C++20, the first thing you need to do is to include the library that gives us access to concepts. And we're going to do that by saying include concepts. This is easy. Now that we have this in, we're going to use the first syntax we saw in the slides. And we're going to add a requires clause after the template declaration. And we're going to say std integral. And we're going to say the template parameter here. I think this is the syntax. Okay, watch what happens if we do this. Down in the code, we are calling the function with char types and integer types. So this is going to compile fine because the concept here is satisfied. This concept is going to enforce for the template parameters we call our function template with to be integral types. Let's build and see if we get to compile successfully. You see build finished good. Everything is going to work, and if we run our program, we should see result A and result B printed out. Let's run the program. We see our result here. Now we're going to comment out the others and leave in the double example, and we're going to uncomment that. And I want you to see the problem we get when we try to use our function template with double variables here. You see, Visual Studio Code is already complaining. It is saying there is something wrong. If we look at the problems tab, it's going to say no instance of function template add matches the argument list. But this is really not descriptive enough. But the problem is our concept is not satisfied by calling our function template with double types because we clearly said that we want the function to only be called with integral types. Let's build our program. We're going to pass this through GCC, and we're going to get a compiler error that says that some concept was unsatisfied. And we see in function main use of function tadd with double with unsatisfied constraints. And this is really clear. When we see an error like this, we will go and look at the constraints that the function has, and we're going to see if we satisfied those constraints by calling like we did in the main function here. And we will know that the function doesn't support non-integral types, and we will fix this problem. This is really how concepts can help in writing safer function templates. Now that we have seen the first syntax, I think it is big time we looked at the other syntaxes. So let's do that. Let's copy the code here because we're going to be reusing this a couple of times and adapt it instead of typing this entire thing. The second syntax involves getting rid of the requires clause altogether and just using the concept instead of type name here. So we're going to say std integral, and this is going to be enough. This is going to tell the compiler to enforce this concept for this function call for all the template parameters that go in the place of t here. I hope this makes sense. Now if we go back, you see that we still have our squiggly lines here. If we try to compile, we will get the same compiler error. Okay, and you see we have the same compiler error, function add t called with unsatisfied constraints. I think if we go down, we're going to see even more stuff out of this. It's going to say required the satisfaction of std integral with t, but now we are trying to call this with double. So this is really going to lead to a compiler error. So this is the second syntax, and it is going to do the same thing. Now that we have seen this, we also have a third way we can do this, and that's through the auto mechanism. Let's set up our function using auto. So we're going to say auto add, auto A, and auto B. We have seen that we can do that in the last chapter, and we're going to return A and B, A plus B I should say. If we do this, you see that the squiggly line goes away, and we can add these things up and print the result. The return type is going to be deduced by the compiler automatically. But know that this is going to generate a function template behind the scenes. This is just a nicer syntax we have to use auto to set up functions that work for multiple types. Let's build and see how GCC handles this. The build is good because we have no constraints here. And if we run our program, it's going to work. It's going to give us 13 as the sum of 11.1 and 1.9. But we can also place constraints on this function here. And you do that by specifying your concept in front of the auto keyword here. So for example, we can say std integral and std integral for the second parameter here. Let's say that. And once we do this, if we go down, we should see our squiggly line on the call of the function here, because now the way we are calling this function is not valid. The function clearly says that it wants to be called only with arguments that satisfy this concept here. If we're trying to build again with GCC, we're going to get the same compiler error. Let's do that. And it's going to say use function with unsatisfied constraints. It's the same error. And if we go down, we should see that it requires the integral concept to be satisfied here. So this is the third syntax you can use if you happen to be using the auto syntax for your function templates. Let's comment this out because we still have another syntax we need to learn about. This is going to be our syntax 3, and we're going to comment this out. And the last one involves just leaving in our function template. Let's copy this because I don't want to type this again. We're going to go down and say syntax 4 and put in our function template. We're going to take this requires clause, we're going to cut it out, and we're going to put it after the function parameter list like this. And this is going to be valid C++ syntax to enforce a concept on your function template. If we go down, you see we have this wiggly line, and I should prove that this works with other integral types here. let's just comment out the double line here and uncomment the other we had for car and ent. If we try to build this program now, it is going to build fine because the constraints are satisfied. But the moment we uncomment the calls with double types, we're going to get a squiggly line, which is a good warning that we have a problem. But if we ignore the squiggly lines and just build with GCC, we're going to get the same compiler error. And it's going to say that to call our function, we need to satisfy the integral concept for the arguments that we pass here. And the double arguments we're passing in here are violating our concept, so we get a compiler error. This is really how you can use concepts in C++. I tried and came up with simple examples to show you different syntaxes you can use concepts with. And this is really it. Try to get yourself familiar with these syntaxes, and it's not going to be really hard to use concepts in your C++ programs. Okay, this is really all I had to share in terms of the syntaxes you can use with C++ 20 concepts. If you go to the documentation, you're going to have more information about this, but we're going to do a few more lectures to really drive these things home. For now, you can come to CPP reference here and see more concepts that you can use. We have a lot of this, and we can really use this to tune our function templates however we want. Okay, for example, you see our integral concept, you see a floating point concepts, and there are even more that are usable with classes, but we haven't learned about classes yet, and we will do that starting in the next chapter. But now I just want you to be familiar with concepts that were introduced in C++ 20. And here is another piece of documentation you can look at just to complement what we are talking about in this chapter, but I wouldn't recommend reading this just yet because it's just going to confuse you. There is a lot of things we still need to learn to really be able to understand this. So try to go through this chapter, and I am going to try and break this down in ways that you can understand this. The main message is that there are more concepts here you can try in your C++ code if it makes sense for the problem you are trying to solve with C++. We are going to stop here in this lecture. In the next one, we're going to show you how you can set up your own concepts in C++. Go ahead and finish up here and meet me there. In this lecture, we're going to see how you can build your own concepts. And this is going to bring us into the second part of concepts we can use in C++. In the last lecture, we used the concepts from the standard library that are built into the C++ programming language starting in C++ 20. In this one, we're going to be building our own concepts. And without waiting anymore, let's see how you can do that. And this is the syntax you can use to do that, and it is really simple. The way you do that, you say a template declaration specifying the template parameter you want to constrain, and then you say concept. You say the keyword concept, you give your concept a name, you put the equal sign after that, and then you're going to specify the requirements for your concept. So for example, here we are using a type trait to specify that this type trait is going to determine what works for this concept here. And what this is going to do is to enforce for our template parameter to only be integral. If it's not integral, we're going to get a compiler error. And one thing I should tell you is that the std integral concept is exactly built like this in the C++ standard library. This is really cool. So if you want to set up your own concept and you want to do that using type traits, you can do that like this, and it is going to enforce for your template parameters to satisfy that type trait. Or to be exact, the concept is going to be satisfied when the type trait evaluates to true. If the type trait evaluates to false at compile time, the concept is not going to be satisfied. That's another way to look at that. Down here, we have another syntax we can use if we have multiple statements in our concept. All you have to do is specify the concept keyword, you give it a name, you put the equal sign, and then you add a requires clause. The requires clause is going to specify the template parameters for which you want to enforce your concept, and then you're going to put a pair of curly braces, and inside that you're going to specify the syntax you want your concept to satisfy. For example, here we want for the two parameters to be supporting the multiplication operator. If this multiplication operator is not supported for the template parameters that we pass, the concept is going to fail. And again, I should emphasize that this doesn't check for the value of A multiplied by B. It's just going to enforce for the syntax to be supported. So for example, if you call a function template with this concept and you try to pass in integers, it's going to work because you can multiply integers. But if you pass two strings, this is going to fail because it doesn't really make sense to multiply strings. Okay, this is the syntax. Now we only have one statement to enforce inside, but if you want, you can even put more statements. If you go down here, we have another example called incrementable. This is going to require for the template parameter to be incrementable. We specify the concept keyword, we say the concept name, we put in our equal sign, and then we say requires, we put on template parameter and put in our requirements. For any template parameter that is using this concept, the syntax here must make sense. So you must be able to take the value that you get from here and, for example, say I plus equals 1. This is going to be valid syntax. You're going to say plus plus A and plus plus B. All these are going to be valid C++ syntaxes for the template parameter that you try to call this function template with. And if this doesn't work, you're going to get a compiler error because your template argument isn't really satisfying this concept. So this is really how you can set up your own concepts in C++. Once you have your own concepts set up, you can use them like we have been using the other concepts from the C++ standard library. For example, we can use syntax 1 to put a requires clause and say that we want to satisfy our own concept. With this particular syntax, you will have to put in these angle brackets and put your template parameter inside. This is the syntax you have to use. You can also use syntax 2 and specify my integral directly in these angle brackets in your template declaration, and this is also going to work. We can even use this with the auto syntax for our function templates. It is going to work. Okay, now that you have seen this, I think it is time we headed over to Visual Studio Code and play with this a little more. Okay, here we are in our working folder. The current project is building your own concepts. We're going to grab our template files like we always do, and we're going to put them in place. And we're going to open this thing in Visual Studio Code. Let's do that. We have our project open here, or folder, I should say. We're going to clean this up a little bit, and we're going to include our concepts library, and we wanted to set up our own concept. The first syntax we're going to see is by using type traits, and we're going to say template type name T, and we're going to say this concept we want this template parameter to satisfy. We're going to say concept, and we're going to say my integral, which is going to be the name of our concept. We're going to put an equal sign, and then we're going to say std integral v and specify that we want this type trait to be satisfied for this concept here. And after this, we need to put in our semicolon, and I think we need to include the type traits library because we are using that. We should say std is integral. So sorry for that. And this is going to work now. Okay, now that we have the concept set up, we can use it like we have been using other concepts. For example, we can set up a function which is going to add up two numbers, and it is going to use this concept here. We have multiple syntaxes we can use. So let's go down and try this out. We're going to say template and say type name T, and we're going to require this concept to be satisfied for our function template. We saw that we could use the requires clause here and say my integral and say the template parameter we want to enforce this on. And after this, we're going to just put in our function template. We're going to say add what we have been doing all along in the last lecture. We're going to say TA and TB, and we're going to return A plus B. Now, this function is going to support our concept. Let's go down and set up two variables. We're going to say int x, and we're going to say 6, for example, and int y, and we're going to make this a 7, why not? And we're going to say add x and y. Once we do this, you see that we have no problem because the concept is satisfied. For the arguments that we are passing in here, the concept is satisfied because the type trait here is going to return true for this type here because it is an integral type. When the type trait returns true, then the concept is going to be satisfied. If the type trait returns false, the concept is going to fail. Let's try and build and really drive this home. You see that the build is good, our function is working. So the function template instance for this call here is going to be successfully generated, and we're going to call it when the program runs. Now, let's change the type of these guys to double and try to violate our concept and make it fail. Once we do this, you see the call here has a squiggly line, and a Visual Studio Code is not going to say that it is a concept problem, which is a shame. But we can still run this through the compiler, and the compiler is going to tell us what is wrong. So it's going to say use of function add with unsatisfied constraints. And if we go down, we're going to see the exact constraints we violated. And we're going to say required for the satisfaction of my integral with t. We are calling this with double, and double is going to evaluate this to false. Hopefully you can see that you can really set up your own concepts using this syntax here. And we can use our concept with all the syntaxes we have seen in the last lecture. So for example, we can take out the requires clause altogether here and say my integral in the template declaration here. So we're going to say my integral. And if we do this, we're going to fail again because the concept is not going to be satisfied. We're going to have the same problem. We can change the syntax to use the auto syntax, but before we do that, let's change this back to type name t, and then put our requires clause after the parameter list of our function template. We're going to say requires, and we're going to say my integral, and specify the template parameter. And this is a valid function template with a concept applied to it. And if we build again, we're going to get the same compiler error. So you see the same error, and we can use the auto syntax. Let's do that. We're going to take out the template declaration here. We're going to take out the requires clause here, and we're going to change our t to auto. And the way we do that, we're going to say std. No std. We are using our own concept. So we're going to say my integral auto. This is going to work. And we're going to say my integral auto and my integral auto here. The moment we do this, you see that we have squiggly lines here because our concept is violated. But if we try and build again, we're going to use GCC to do that. The build is going to fail. You see that the same concept is violated, and we are able to use our concept throughout the 4 syntaxes that we saw in the last lecture. And this is really cool. Now that we have this, we're going to comment this out, and we're going to see that we can set up concepts that have requirements spanning multiple statements or multiple lines. Okay, let's go down and do that. Suppose we want to set up a concept that is going to enforce for the template parameters to be multipliable with the multiplication operator we have here. We can use this syntax here. We're going to put in our template declaration, we're going to say concept, we're going to say the concept name, we're going to put in an equal sign, and then we're going to put in a requires clause with our template parameters n. And after that, we're going to put a pair of curly braces, and inside the curlies, we're going to put the requirements. For example, in this case, we require for the template parameter here to support the multiplication operator between 2 of these types. If the multiplication operator is not supported, we're going to have a problem. And this is the concept that is going to enforce that. One thing you should know is that this is just going to check that multiplying a and b is valid syntax. It's not going to check the value of a multiplied by b, and you should really understand this. Now that we have this n, we can set up a function to use these 2 guys. Why not use the function we have seen before to add 2 numbers? Let's do that. And we're going to put in our requires clause, and we're going to require now to support the multipliable concept, and we're going to specify our template parameter. We have the concept n, so we can use that to do whatever we want. Now we're going to say t add, and we're going to say ta and tb, and we're going to return a plus b. This is the same function we've been using all along. Okay, now we have our concept in place, and we have a function template that is going to use this concept. Let's see if we can add up x and y and see what we get. We're going to build with GCC. We're going to see that the build is going to be good because our concept here is satisfied. We are passing double types for our function template, and it is legal to multiply two double variables. If we multiply two doubles, we're going to get a value, and that's going to be valid C++ syntax. But let's see what happens if we try to change our arguments to std string. Let's do that. So we're going to say x is hello, and we're going to say y is world. Why not? Let's go down and put in our semicolon. And the moment we do that, you see that we have a problem. And Visual Studio Code is not good at this yet. But if we go inside and run this through GCC, we're going to get that our concept is violated. Let's look at the compiler error here. It's going to say constraints not satisfied, and it's going to tell us that we are calling the add function with values that can't be multiplied. It's going to say the required expression here is invalid. And this is how you can set up a concept like this. And you can really use this to put constraints however you want on your function templates. But here we have just used one statement inside our concept here. We can even put in more. So to drive this home, we're going to set up another concept. Let's go down and put that in place. The concept is going to be called incrementable. It's going to be using the same syntax we saw here, but we're going to be putting a requirement on the template parameter here to support incrementation. And we want for every type that goes in the place of t here, we must be able to say a plus equals 1. This must be valid C++ syntax. We must be able to say plus plus a. This must be valid C++ syntax. And we must be able to say a plus plus. This must be valid C++ syntax. Now that we have this, we can change our add function to use this concept. Why not? We're going to say incrementable. And now this function is going to be required to use things that we can increment on. And you see it is failing already because we can't really increment strings. What does that even mean? So let's build and show you the compiler error. Okay, you see incrementable is not satisfied, and the required expressions aren't valid. You see plus plus a is not valid, a plus plus is not valid, and a plus equals 1 should not also be valid, but we're not seeing that here. But hopefully you see the message here that our concept is failing here. If we comment out our strings here and uncomment double, all these operations we have here are supported for the double type. So we should not fail here if we try to compile this because the concept is going to be satisfied. Let's use the GCC compiler to build. You see the build is good now, and we can clear and we can bring up a terminal to really see this, that our binary was generated. Let's do the IR. We're going to see our rooster executable here, and if we go down, let's say done, we're going to see that if we build again to bring this in consideration, clear run rooster, the program was generated and it is really running because the concept here is satisfied with our call using double arguments here. Okay, so this is really all I set out to share with you guys in this lecture. I hope you know the syntaxes you can use to create your own concepts. You can either use type traits like we have seen here, and the syntax is to put the keyword concept, put in your concept name, put an equal sign, and then specify your type trait here. This is going to work. If you need something a little more complicated, then you're going to use this syntax here and put the requirements for your concept in these curly braces. You can either put one statement like we did here, or you can even put as many statements as you want. Just remember to end them with semicolons. And another thing you shouldn't really take lightly is that this is just going to check for syntax. It's not going to check for the value you get after you add 1 to a here, for example. It's not going to check for the value you get after you multiply b. It's just going to see that a multiply b is valid syntax for the types that our template parameter is using here. We are going to stop here in this lecture. In the next one, we're going to zoom in a little more on the requires clause here. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about some more things we can do with our requires clause. But before we do that, let's look at the kinds of requirements we can put in our requires clause. The first one is a simple requirement, which is what we have seen so far. We can also do a nested requirement, and we're going to learn about this in a minute. And we can do a compound requirement, which is going to allow us to specify more things about what we require for our concept. There are also type requirements, but these are really advanced for the scope of this course, so we're not going to talk about these in this course. What we're going to look at are these three first here. So let's look at a simple requirement. This is what we have seen already. Here we have our template declaration. We have a concept declared. The concept name is TinyType. We're going to put in our requires clause. We're going to put in our parameter list, and we're going to put in our curly braces. Inside the requires clause, we have a statement here, which is going to enforce that size of t is less than 4. And what this really means, it's going to check that size of t, the syntax here is correct. And this can really throw people off. I have said this in the last lecture, but I set up this little example to really drive this home and show you that if you are not careful, your concepts are going to be really wrong. This is going to check for the syntax. So for example, if we call a function template with this concept with a car type, the concept is going to be satisfied, even if the size of a car is less than 4, obviously, but that's not going to be the job of this concept here. This concept is not going to enforce for the expression here to evaluate to true. It's going to just check the syntax. And if you pass something smaller than an int in a function template with this concept, this is going to be valid C++ syntax, so the concept is going to work. So now you must be asking, how can I enforce for the value of this expression to be true using concept? Well, for that, you will have to use nested requirements. And a nested requirement is going to have another requires keyword inserted in front of it. Now, if you use the syntax like this, now this is going to check that size of t is actually less than 4. If it's not less than 4, this is going to return false here, and the concept is going to fail. And this is how you can use nested requirements to enforce for some expressions to be true in your requires clause. Another kind of requirement you can set up for your concept is the compound requirement. And this is going to allow you to check if something doesn't throw an exception. You can do that using the no except keyword, but we're not going to use this now because this is not in scope for what we can do at this point in the course. But you can also check the return type of an expression and enforce that it satisfies some type trait, for example. So here we are saying for our concept, and if we pass in 2 parameters, the syntax for adding A and B must be correct and supported for those types. But the result of A and B must also be convertible to int. And you can do something like this. And this is going to work. You can enforce these kinds of things using compound requirements. Okay, now that you know about these kinds of requirements you can put in your requires clause, let's head over to Visual Studio Code and play with this a little more. Okay, here we are in our working folder. The current project is zooming in on requires clause. We're going to grab our template files and we're going to put them in place. And we're going to open that in Visual Studio Code pretty quick by dragging and dropping here. This is going to open up our folder. We're going to do the usual. We're going to close the pane here. We're going to clean things up a little bit. And we're going to include our concepts library. Let's do that. We are going to set up a simple concept. We're going to say template, and we're going to say what the concept is. The concept is going to be called TinyType, and we're going to say what makes this concept a TinyType. We're going to put in our requires clause, and we're going to put in the template parameter, call it t, why not? And we're going to put in our closing semicolon here. Now, what is going to make this concept a TinyType is that the size of the template parameter here is going to be less than 4. Let's suppose we are doing a function and we want it to use for integral types that are smaller than 4 bytes in memory. Suppose you want to do this, and it is useful in the problem that you are trying to solve in C++. The way we can enforce this, we can say size of t is supposed to be less than 4. Let's say size of properly, can't type can I. Okay, the moment we do this, you're going to see that this is valid C++ syntax, so we're not going to have any squiggly lines, but what you should know is that this is a simple requirement in C++ concepts. And what this is going to do, it's just going to enforce the syntax of what we do here. What we put here must be valid C++ syntax. So only enforces syntax. This is what you should really remember. Okay, now that we have this in, let's try it out and show you some problems you can really run into. We're going to set up 2 character variables. We're going to call the first one x. We're going to initialize this with 57. Why not? 67. And we're going to put in the other variable, which is going to be y, and it's going to have a 56n. You can put in whatever you want. Just make sure that you are within the range of a card type, which is between 0 and 255, if you remember. Okay, now that we have this n, I realize we don't have a function. We can try this on. Let's set up another function pretty quick. We're going to say tiny type auto. We can do that. You already know this syntax. And we're going to say add tiny type auto a and a tiny type auto b. We can do that. And we're going to return a plus b. Now that we have this, let's say a and b down here and call this function. We're going to say x and y. And we're going to try and compile this program. And it is going to compile fine because the type we are using to call the function, which is char, its size is going to be less than 4. Okay, so this is going to work and it is going to compile. Let's build with GCC. You're going to see that the build is good. Let's try and change the type here to int or even double. You know, double is 8 bytes in memory. So we expect this to probably give us something wrong. Double type is 8 bytes in memory. So we expect the size of t here to be false because the size of t is going to be 8 and 8 is not less than 4. This is going to be false. So some might expect this concept here to fail, but let's try and really prove you wrong. We're going to build with GCC and you see it's building successfully. What this is really doing is that with simple requirements like we have here, C++ is only going to enforce for this to be valid C++ syntax. And size of t is less than 4 is going to be valid C++ syntax even if this expression here evaluates to false. This is not going to enforce for the value of this expression to be false. You can't do that with simple requirements. What you will do is check that this is valid syntax. Now, what do we do if we really want to enforce that size of t should be less than 4? If you want that, you should use nested requirements. And the syntax to do that is really simple. We can go down here and put that in. We're going to say requires. We're going to add a requires keyword in front of this. Then we're going to put our expression here. Let's copy it and put it in. I don't want to type this again. The moment we do this, now compilation is going to fail if we pass a type whose size is not less than 4. And let's try and build again. You're going to see that the build is going to fail now, and we're going to have a failed concept. And you see build finished with errors. We have constraints not satisfied. And if we go down here, we're going to see required for the satisfaction of tiny type auto. And we passed in a double type whose size is 8 bytes in memory, and it is less than 4 bytes. You see the requirement here. It is not satisfied. We can do this using nested requirements. Okay, if we go down, for example, and change this to char, some people call this char, but I call this char. That's my habit. If we change this to char and try to build again, you're going to see that it is going to build fine because now, what is wrong here? Let's see what we got wrong. We are getting a compiler error here. What is the problem? It's going to say, let's go up and try to analyze this a little bit. It's saying deduced return type does not satisfy placeholder constraints. And we are requiring for the return type of this guy to be tiny type. I think I know what the problem is. The problem is the arithmetic operations like the addition we're doing here are not supported for types which are smaller than int. Int is the smallest type we can use with arithmetic operations. So what the compiler is going to do is going to do implicit conversions from char to int. And inside here, what we will have are going to be int. The result of this is going to be int, and the return type is going to be deduced to be int. But int is going to violate the requirement we have here, which is saying that the size of tiny type here should be less than 4, and the return of int is not less than 4. So we can try and fix this by putting an equal sign here, and I think it's going to work. Let's do that and build again. This is a good learning experience. And now you see that the build is going to work because now the return type is going to satisfy our requirements. So let's prove that we are getting an int out of this actually. We're going to do auto result, and we're going to say equal and grab the result of this guy. We should really prove these things. And after this, we're going to print the result. We can do that. And we can even go further and print the size of result here. So we're going to say size of result. Okay, now that we have this n, we can build with GCC, and the build is good. Don't mind this squiggly line. It is probably Visual Studio Code messing with us. You see that the build is good. We can now bring up a terminal and run this and see the size of the return type and really prove that the compiler turned that into an int, even if we called our function with char arguments. This is interesting. So clear and run rooster. Now we're going to see result is going to be 123, and the size of the result is 4, even if we passed in char types as our arguments. Okay, so hopefully this proves that you can set up nested requirements to enforce for the expression here to be checked. Another type of requirement you can do is a compound requirement. Let's put this in, and we're going to put in a simple example to drive this home. I think I should take this function and put that below our concepts. So a compound requirement looks like this. You put your expression in curly's like this, and then you can even put requirements on the values of the expression. For example, we can enforce that the value of a plus b here should be convertible to int. If it's not convertible to int, the concept here is going to fail. This is a compound requirement. You can even put no except keywords in here, but we're not going to go this far because we haven't really learned about exceptions. So for now, I'm going to take this out. I just wanted you to be aware that you can do that. Now that we have this concept in, let's play with it and see how we can make it break things. We're going to change our concept to addable. Let's say addable here, and we're going to say addable, and we're going to put in our char types here, and it is going to still work because we can add 2 char variables, and this is going to work because we can add 2 char variables, and this is valid syntax. What we're going to get out of that is going to be an int, because remember, the compiler is going to insert implicit conversions from char to int because it can't really add 2 char types. Int is the smallest thing you can do arithmetic operations on. So the result of this is going to be an int. So an int is convertible to an int. This is going to work. Let's build and show you that this is going to work. We're going to build this with the GCC. You see, build is good. We can try and run this and see what we get. After calling the function, we get result is 123, and this is going to be the size of 4 because we get an int out of this. Let's try and change this to double and see what we get. So double, let's say double here. And if we build, we expect this to work because adding up 2 doubles is going to give you a double. And we're going to return a double from this function, and a double is convertible to an int. So we're going to return a double from this guy, and this should say 8 now, because that's what we are returning from the function here. Let's build with GCC. You see, the build is good. We can clear and run rooster. This is going to say size of result is 8, because now what we are returning is going to be a double from this function here, and double satisfies our concept. Adding up 2 doubles is valid syntax, and what we get out of that is going to be a double, and a double is convertible to an int. This is going to work. Let's try and change our parameters here to string. We're going to comment out our x and y variables here, and we're going to set up 2 strings. We're going to say std string x, and we're going to say hello. And you know what we're going to say in y? We're going to say std string y, and we're going to say world. Why not? And the moment we do this, you see that we have a problem. Why do we have a problem? Because it is now a requirement for the result of A and B to be convertible to int. Remember that you can add up two strings. For example, you can say auto s and say x plus y. This is going to work because you can add up two strings and this is going to concatenate them. So this is valid syntax. Why are we failing here? Because we have a requirement for this to be convertible to an int, and the string isn't really convertible to an int, so this is going to fail. Let's build this program and show you that this is actually the case. We're going to see build finished with errors, and let's see the error we have. Okay, so constraints not satisfied. It's going to say required dissatisfaction of audible with auto here in requirement, and it's going to say A plus B does not satisfy the type requirement, because what we get after adding A and B is not convertible to an int. And you see that here. A plus B convertible to an int, this is going to fail. Okay, so let's try and remove this requirement to convert to int and see that this actually works. We're going to remove this. I'm going to cut this out and try to build again. I am going to use GCC to build. And now you see that this is building because we no longer have the requirement of the return value of this expression, or result, I should say. The result of this function now doesn't have to be convertible to an int. Okay, let's put this back because I want you to see this later as a reference. And now you know how you can use compound requirements to really put constraints on your function templates. This is really all we set out to do in this lecture. I hope you found it interesting. I think I should comment out these guys because I don't like to leave you with code that has compiler errors. Let's turn this back to double so that this works. We're going to build again. Okay, the build is good. And we are going to stop here in this lecture. In the next one, we're going to see how we can combine concepts and do some crazy things. Go ahead and finish up here and meet me there. In this lecture, we're going to see how we can combine concepts using logical operators. We can combine concepts using the AND operator and the OR operator as you see here. Let's look at a simple example. Here we have a concept. It is tiny type we have seen before, and it's going to check that the size of the template parameter we pass is less than 4. It's going to enforce the syntax with a simple requirement, but it's also going to enforce for the value of this expression to be true. If the value is not true, the concept is going to fail, and we are using a nested requirement for this. So this is our concept here. Let's try and set up a function and see how we can combine this concept with other concepts. Here we have a function. It is going to return t. The name of the function is func. It is taking in our parameter. And here we have the body of the function within these two curly braces. But what we have here is a concept we want to apply to this function here. And the first line here is going to show that we can combine concept like we do here. So this entire thing is going to be a logical combination of concepts. So we can require that the template parameter be either an integral type or a floating point type using the OR operator here. Another thing we can do is use the AND operator as you see down here in this second line, and we're going to require that the template parameter is both integral and a tiny type. And the compiler is going to enforce these things as we are about to see in a minute when we hit Visual Studio Code. You can even specify your concepts in place. For example, the third line here is going to say we require for the concept to be integral, so it should be an integral type, and we're going to specify our tiny type concept in place. You see, we are doing that right here in the function declaration. And this is going to work. This is a valid C++ syntax, but I don't recommend this because this is going to make your function declarations really ugly. So now that you know this, we're going to head over to Visual Studio Code and play with this a little more. It's just using the OR and AND operator to combine concepts. Okay, here we are in our working folder. The current project is combining concepts. We're going to grab our template files pretty quick and put them in place. And we're going to open this in Visual Studio Code as we always do by dragging and dropping here. We have our file. We're going to open that up and close the left pane here. I don't like it. And we're going to include our concepts library. Let's do that. We have this n. The first thing we're going to do is to put in our TinyType concept here. So it is TinyType. It's going to require that the syntax for size of t less than 4 be supported. This is a simple requirement again. And we're going to require that this expression be true. And we're doing this using a nested requirement. Okay, now that we have this concept, we can combine this with other concepts. Let's use the same function we've been using all along. So we're going to say template type name t, and we're going to put in our requires clause. So we're going to say requires. We can use std integral and say t and say, or it should be std floating point. I think we have this n. This is a concept we have, which is built into the C++ standard library. We can use this. Now that we have this, we can then say the signature of our function tadd. It's going to add up ta and tb, and it's going to return the sum of a and b. Now, you can only call this function with either integers or floating points. If you try to deviate from this, the concept is going to fail and we're going to get a compiler error. Let's go down and try this out. We're going to say int x and put in a 6, for example, and int y and put in a 4. And we're going to add this up. We're going to say add x and y. And if we do this, this is going to work because this is an integer, so the concept here is going to succeed. Let's build with GCC and show you that the build is good. The build is good, so no problem. We can change this to double. It is going to work because double is a floating point. Let's say double properly. And if we build again, the build is going to go through. But if we try and use, for example, a string, let's say std string, that's a string. And we're going to change this into double quotes. We can do that and say std string and put this in quotes, again, double quotes. Okay, if we do this, you see we have a squiggly line. And if we build, we're going to have violated our concept because the parameters that we pass don't satisfy this concept. It's neither an integral type or a floating point type. And if we go up here, we're going to see that we have violated a concept constraint not satisfied. And it's going to say the concept that was not satisfied here, which is right here. Okay, you can combine two concepts using the OR operator, but we can also use the AND operator. Let's go down and try and put up a simple example that is going to do that. Now, what we're going to require for people to use this function is to satisfy both TinyType and integral. So we're going to say requires std integral. I think we have this n, and we're going to say and TinyType, and we're going to say our template parameter here. The moment we do this, and let's turn this back to being int, let's say int x and put in a 7, what we had before, and int y and say 4 or a 5, doesn't matter. If we do this, let's see our thing again. So TinyType requires for the size to be less or equal to 4. So int is going to work. This is going to build because the concept is going to be satisfied. It is both integral and TinyType. Let's build and see this run. You see the build is good, our concept is satisfied. But the moment we try and use something that is greater than 4, we're going to have a problem. Let's use a double, for example. We're going to change this to double and build. We expect compilation to fail because the type, which is double, doesn't satisfy the TinyType concept. And we're going to see that here. Okay, so we're going to see build finished with arrows, and we're going to have a lengthy arrow here. But the meat of this is that we have a constraint which is not satisfied, and it is that required for the satisfaction of std integral. So double is not going to satisfy this. I think double was a really bad example because it's not integral, so integral is going to fail. What if we pass in long int, okay, which is really an integral type, but it's not going to satisfy TinyType. So let's say long int, and we're going to build. Now we are going to violate, let's use long int, because I think long int is not large enough. So we're going to build. Now we're going to fail because TinyType is not satisfied. you see required for the satisfaction of tiny type, and it's going to say size of t is less than 4 is not satisfied, because guess what? The size of long int is greater than 4. You can try and prove that by taking out this guy here and saying std out size of long int. We're going to see this print out. And if we build now, we're not going to violate our concept because we're not calling the function. The build is going to be good. What we want to do is run the program and see the size of long int. We can do this. Rooster 8, the size of long int is 8, and it is going to violate our tiny type concept. Okay, you can do things like this and combine concepts, but we can even put our concepts in place. We can do something crazy and for example say, let's copy this, and we're going to go down and say requires integral, but we're going to put tiny type in place. For example, we're going to grab the requires clause here and copy it and put that in place of tiny type here. We're going to do this, and you're going to see that this is going to be valid C++ syntax if we take out the semicolon, because it shouldn't be there. But look at this. This is really ugly. This is going to make your functions really hard to read, but it is going to work exactly the same way it did. If we call this function, we're going to violate tiny type. Let's do that. We're going to build with GCC. We have an error. Let's bring this up so that we can see what is wrong. Nested requirement size of t is not satisfied. This is a syntax you can use, but I don't really recommend this because this is going to make your code hard to read. And this is really all we set out to do in this lecture, looking at how we can combine our concepts using the AND operator and the OR operator. And you can really use this in all the syntaxes for concepts we have seen, but I just used this in this lecture because it is simpler to show. We are going to stop here in this lecture. In the next one, we're going to look at concepts and auto. Go ahead and finish up here and meet me there. In this lecture, we're going to zoom in on concepts and the auto keyword. We have already seen that we can do something like this. Use the auto keywords with our functions and let the compiler generate our function template behind the scenes, and this worked pretty well. We could use this syntax to put constraints on our auto keywords, and we saw that the compiler could actually enforce this and throw a compiler error if our concept here is violated. What I haven't shown you is that you can even enforce concepts on variables that you declare. You can do something like this. Set up a variable, say auto x, and call the variable x, and enforce for the variable to be an integral type. I don't really think you have much use for this, because once you call the function and assign a value to a variable, you already have an idea of what is going to come out of the function. But if you have a use case for something like this, please go ahead and use this. It is going to enforce your concepts. You can even use concepts like this. Set up a variable and assign a literal to the variable name using the auto keyword here. But I personally find this useless because you are putting in the value yourself. Why do you want to put a protection if you know that you are putting in a double literal? Then the variable should be of double type. I find this a little bit useless, but it is supported in C++. If you have a use case for this, please go ahead and use this. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Okay, here we are in our working folder. The current project is Concepts and Auto. We're going to grab our template files and we're going to put them in place. And we're going to open this up in Visual Studio Code. Let's do that pretty quick. We're going to have our folder open. We're going to open the main CPP file, close the left pane and clean things up a little bit. And we're going to include our concepts library. And we're going to put in our function, which is going to be using the auto keywords to really make the syntax nice and cool. But we're going to be constraining our auto parameters here to use integral types. If we call this function with something that is not an integer or an integral type really, we're going to get a compiler error. So if we go down here, for example, and say add and say 10.9 and 0.1, we're going to get a compiler error because 10.9 and 0.1 are double literals and we only support integral types in this function here. So let's build and show you the error. But you must know this by now because we have done this like a gazillion times. The concept integral is going to be violated and it's going to say required for the satisfaction of integral. So the concept is failing here. We're going to get a compiler error. But if we change this, for example, to 10 and 5, put in whatever you want, which is an integer, this is going to work. We're going to build with GCC. You see, the build is good. So you can use auto with concepts like this. We have seen this syntax already a couple of times in this chapter. What we haven't seen is that, for example, you can set up a variable in main and call this x, y naught, and say this variable should satisfy the concept and specify the concept you want. For example, let's say std integral. And if you do something like this, let's see what we get from this. We're going to build. You see, the build is good because if we add up these guys, we're going to generate an integer instance for this function, and we're going to deduce the return type as int. So the return type is going to be integral, and it's going to be assignable in our variable here. But if we change to floating point, I think we have this concept in place. Yes, we do. But it is going to fail because what we get from this function is going to be an integer, and we can't assign to this because this concept here is saying what you try to assign to this variable here should be a floating point. This is the meaning here. And if we do this, we're going to get the error probably. So we have the error and it's going to say constraint not satisfied, and it is going to say the constraint we didn't satisfy, which is floating point here. This is how you can put constraints on your variables even when you are declaring them. So another thing we can try here is to assign a literal to this variable here. Let's put in a 3.9 and see if this actually builds and compiles. Let's build with GCC. You see, the build is good, and the requirement is for what we assign to this variable here should be a double. And a 3.9 is already a double, so no problem. But if we try and make this a 7, for example, this is going to fail. So let's build again. You see, the concept is going to fail. And this is how you can use these things to constrain your variables. I personally find this a little bit useless, at least in this case here, because I know that I have an integer literal and I am assigning this to a variable. Why do I need the help of concepts to really constrain my variable here? But in the case where you are calling a function, for example, using a 5 and an 8, this can come in handy because it's not easy to keep track of the return type you get from a function. Because a function might have a return expression that has multiple different variables, and it's not easy to keep track of what you get back from a function. And you can use a constraint like this to make sure what you get from the function is what you want. And if it's not what you want, you're going to throw a compiler error because the concept you used is going to fail. I would like to welcome you in this new chapter where we're going to be learning about classes. Classes are a mechanism we have in C++ to build our own types and use them like we have been using other built-in types like int, double, or whatever. And we're going to be able to do that by setting up blueprints of our class types, and we're going to be using those blueprints to build actual objects that we can use in our C++ program. So for example, we can have a class as a blueprint, and we can create real class objects in our C++ program as we need them. And we're going to be learning all about this in the next few chapters. We are going to head over in the next lecture and let you set up your very first C++ class. Go ahead and finish up here and meet me there. In this lecture, you are going to build your first C++ class. Classes are a mechanism we have in C++ to be able to build our own types. If you remember, so far in this course we have been using basic types like int and double, and we were using them like this. We said the type of the variable, we give the name of the variable, and then we initialize this variable, and we can use this throughout our program. Now we are at a point where we need to start designing our own types. Suppose we want to build our own type that models a person, for example. Suppose a person is defined by the name, the age, and the address. And we want to model persons in our program and use them as players, for example. And when we have the properties of a person, we can do all kinds of crazy things with them. We can make them jump up, for example, if we are designing a game. We can make them run. We can make them fly. We can do all kinds of crazy things. In this lecture, we're going to use a cylinder as an example. And we're going to model a cylinder in our C++ program. A cylinder is defined by two things. It has a base radius, which is modeled by this r you see here, and it has a height. And when we have this information about our cylinder, we can really do all kinds of crazy things. For example, we can compute its area, the base area, and the formula to do that is pi r squared. This is a formula you get from your basic mathematics education. You can compute the volume of the cylinder, and the formula to do that is area multiplied by the height. And we can really do all kinds of crazy things with the cylinder if we have this information. So we're going to use this information and model a cylinder we can use in our C++ program. And we're going to be using classes to do that. The syntax to set up your class in C++ is really simple. You say class, this is the keyword you have to put in here. You say the name of your class, in this case it is cylinder as you see here, and then we put a pair of curly braces in place. The start is on top here and the end is down here, and after your class definition you're going to put a semicolon. Inside the class we really have two parts. We have member variables which are going to model the properties that your class is going to have. In this case, we have two properties that really define a cylinder. We have the base radius and we have the height. We have decided to model these things as double types inside our class. And this is going to make the first part of our class, the member variables. The second part is going to be made of behaviors or functions that do things on the class using the properties. And one function we have is the volume function, which is going to help us compute the volume of our cylinder here. If you look at its syntax, it really is a function. We have a return type, we have the name of the function, we have the parameter list, which is empty by now, and we have our curly braces that delimit the body of our function. Inside the function, we're going to do nothing special. We're just going to return the volume of our function here. And if you remember, the volume is the base area multiplied by the height. And this thing here is going to model the base area. You see it's pi multiplied by the square of the radius. And then we're going to multiply this by the height. And we're going to return the volume for use by whoever is calling this function. One thing we haven't really talked about is this public thing you see here. And what this says is that the members that we have in this class are going to be accessible from the outside of the class. For now, we can't really understand this, but when we hit Visual Studio Code, I'm going to show you what this exactly means. Now that we have the class declared, we can really use it like we use any other types in C++. For example, we can head in our main function and set up a variable called cylinder1 as you see here. Its type is going to be cylinder, and notice that this is really a type that we build ourselves, and we can really use it like we use other variables. For example, we can call its function using the syntax here and print the volume. This is going to print the volume using the volume function that we just set up in a minute. If we go down, we can modify things about our cylinder. For example, we can use the dot notation here to change the base radius and change the height. And if we try to print the volume again, this information is going to be picked up and be used by the volume function to compute the volume of our cylinder here. This is really cool. If you want, you can also set up another cylinder like we do here, and we're going to print the volume. And we can really do all kinds of crazy things with our types like this. Okay, this is our class, and we can really use it to do a lot. Before we head over to Visual Studio Code and play with us, I want to bring to your attention that members of a class are private by default. And what I mean by that is that, for example, if we don't put these public keywords in here, we won't be able to use the volume function, for example, like we have used it in our main function, as you see here. If the member is private, it won't be usable outside the class. This is what we mean here. We are trying to use this member in the main function outside the class definition. It won't be accessible if it is private. And we make it public by putting the public keyword and a colon like we do here. Everything after this public keyword is going to be public until we change this to private somewhere in our program if we need that. Now that you have an idea about how you can declare and use your class in C++, let's head over to Visual Studio Code and play with this a little more. Okay, here we are in our working folder. The current project is your first class. You are going to build your very first class in C++. We're going to grab our template files. We're going to copy them and put them in